Okay. Should we go to the paper directly, or should we?
You can also skim the Twitter.
Oh, I was going to say the blog post, but we can also skim the Twitter first.
Yeah.
Do you have the Twitter link in hand? Oh, there, I see. Let me put it here. Yeah, I guess maybe. Although, okay, I'm curious why they did this. Is this a I haven't read the paper or anything, but is this a technique that only works on vision models? Or like, I mean, is there some reason why I'm not doing this kind of thing for LMs or whatever?
That's a good question, and I wonder as well.
Is this another trick that is still not the true unsupervised finding of manifolds inside models thing? Oh, you were
in general.
They do it on some toy models and lanes that aren't vision, so I assume it can generalize. They just chose vision models because it's easy to visualize. That's my guess.
Okay, makes sense.
Let's see. Like, I would assume unsupervised manifold discovery would work for any deep learning systems, but let's see. Yeah.
Or also, is the other paper also on visual models, or is it something else?
I'm quickly sending.
Oh, actually, the other one is not. Is also on LLM, so that's nice. But yeah.
Sort of like.
So.
Oops! I posted. Whatever.
What happened?
I noticed I accidentally made a tag for a reading group in Slack, which doesn't exist in Slack.
Doesn't matter. Okay, so first and code semester assumption. Yeah, toy data. Yeah, but that's not toy data. But there is some real data that has some activations that look like this. It doesn't work well. Subspaces that tend to activate together in this direction.
Wrong. Okay, I should also close the blog post.
Alright, so yeah, I don't know what everything is people. Yeah, I guess we can start it. Yeah, so the Twitter thread is mostly they trade on visual models. I don't know much about what the best visual models are.
I guess vision transformers are basically replacing CNNs.
Everything is transformer now. Then
yeah, I just yeah. Well, I just looked at the paper not from distance on like the how to make vision transformers work. Like initial, it's called Dino. I looked, yeah. I think that one is also used in practice because it allows you to do self-supervised learning.
Okay. That's a manifold. By the way, doesn't this? I guess maybe this will be on the what on the interview on machine learning street talk maybe.
Yeah, they will discuss more broadly.
Yeah, but I was saying that this seems like
Mech Interp.
there people were having like, there was this previous paper they liked, the one with the this seems to show the thing I was saying of what the paper is wrong. The one with how the models, like the models trained were getting the didn't have sensical changes when you move through the space, but when you actually find the right geometry, they do.
Oh, you mean fracture entanglement representations? Yeah,
Yeah.
I looked By the way, when I looked this Saturday at one vision paper that was doing a very naive form of Mech Interp. They just plotted the attention maps, and even that was enough to see that the model was paying attention at coherent objects in the image, which is fascinating. Like emergent segmentation, essentially, in the attention maps. That itself looks to me like a very neat fact that identify representations, but I don't know. It depends, I guess. It's one perspective. It's just literally naively plotting attention maps. Well, they did some more math. It's not just that, but yeah.
I guess we can
But
go to
yeah, I think it's still true to some extent. But maybe a lot of the results are artifacts of assay features, of assays, for example, when you have duplicate features or feature splitting, then that's maybe because of assays and not because of the model. Who knows? Or maybe both.
I mean, some are because we then do the manifold thing, and then you find whether splitting or whatever. I think I saw it on the source ones. Yeah, here on the other paper says that doing this reduces feature splitting, absorption, all that.
Wait, is this in this paper?
No, this is the other paper, like the one we were saying.
Yeah, the one we read before.
No, we didn't
Or
read this one.
Subspace.
This is just another similar paper that seems to be doing a very similar method, not the same that came out at the same time.
Yeah, I remember even in the entropic paper, I think it was the rotating manifolds, the geometry of the geometry of line counting task where they use the rotating manifolds things. I think that they made some correspondence between the manifolds and the assay features.
Yeah.
Where the assay features style the manifold. Yeah.
Yeah, there was the previous Woodfire papers that they were talking about that.
Yeah.
Okay, I guess we not sure if I should skim the blog post or go directly. But let's go to the paper directly, I guess. So yeah, for everyone else, remember that it doesn't have to be. I mean, you don't have to talk if you don't want to, but it doesn't have to be Bernie and me talking for hours. You feel free to interrupt at any moment and say things. I'll be going through the paper. I partly do that because otherwise nobody says anything. But yeah.
Tell us how wrong we are.
You want to say something, or you didn't understand something and you want to look more into it or something, we can do that. This is supposed to be a reading group, not the Victor and Bernie podcast. On the right, we showed. Okay, so going back to this. Is it me, or is it kind of weird to have a figure at this, like on top of the abstract?
I see that few times. The other paper from Saturday I looked at today had that as well.
I guess it's not necessarily bad design. Like it looks nice. Maybe it's better, like to have some cool picture on the top. so it's more nice or something. But I don't know. Let's read the answers.
Interesting. Rabbit ears manifold, rabbit face manifold, a C direction.
What's geometry of favorite percent? Yeah, so okay, it seems weird that they are doing it for images, right? But you don't need to. Okay, to improve sparsity, which groups directions into blocks.
Let's see if in future work they mention language.
This other paper is apparently about GPT-2 and Mistral already. You know, I don't know if it's the same method or a slightly or a similar but different method that we'll see. Maybe this one is tuned for vision.
Hearing diffusion models. Pretzel manifold.
We
Oh,
implement 3 variants of Block-Sparse Featurizers, and through a minimum description length analysis show that all 3 describe activations more completely than iteration-based Featurizers. Huh.
ooh, they recover the Inception V1 curve, I think. Oh yeah, I remember that from the Twitter thread.
What's that?
They
okay.
yeah, we can look later.
Do you know what this Ascension D1 thing is?
It's some old PNN, I think.
People have found curve detectors, but they seem factual.
Yeah. It's an ancient CNN from 2014.
Okay, that's very ancient.
That's from before the Big Bang.
But still less ancient than some of the
Which came from yeah. Which came from Linet from Lekun. Well, Lekun stole everything from Schmidhuber, obviously.
For the observatory contact or images and different models via manifold steering. Okay. And it's calling over the manifolds. Okay, that's nice. So yeah, this is basically what I think is the
It groups
block.
directions into blocks.
And I don't know how it works yet, but it's like not the same kind of finding manifolds somehow, and it's kind of like sparse encoders, but with manifolds, I guess. It involves blocks or something. Sorry, someone posted on chat. Oh, nice. Ryan says that they been running on chat. I mean, that they've been running the BSF experiment. And yeah, that looks nice. It has some samples with.
Yeah, I don't have any like super interesting conclusions other than like some, I don't know, just like funny things happening.
Yeah.
Yeah, I see different number of apples where you're trying to find some manifold for the number of apples or something.
Yeah, for like count.
Oh, I see.
Just trying to like find other stuff, like, or to like isolate more interesting things. But like the pretzel stuff, like, I don't know. I wanted to find like anything that was like related in particular to anything with like shape of objects. But this is like way more difficult. It seems like, and you know, that's probably very complicated shapes.
Yeah, in this paper they found some, I think, lighting or something like that.
Yeah, I think style was like one of the easiest things.
I wonder a problem with things like count is that the models are not very good at it. You know, like I think a lot of the image models, even if you like I don't know the classifier the models that are like Like the models that generate images, usually when you prompt them, then you tell them whatever number of things. It doesn't. They don't always produce that number of things. So yeah.
Yeah, that's true. But maybe you could find some manifold anyway. Like this makes me think there are some ancient like techniques where you there are essays on diffusion models, so you can do I think even something like vector steering on diffusion models, which I'm not surprised. That should obviously work, I think. So I'm not surprised this also works. This manifold stuff. Also, I looked at the abstract. I see a representation is a sparse sum of low dimension manifold. So it is not just one manifold is a sum. So do they mean union? Because that would mean they are enjoyers of union manifold hypothesis or something like that. I don't know. I wonder what do they mean by sparse sum of low dimensional manifolds. I guess because you can compose different manifolds, like the cat manifold and I don't know, number of legs manifold or something. Let's see, what do they mean by that?
This is the this typical thing about why first encoders are bad and why this method is good.
Their virgin method versus our Chad method.
Base possesses manifolds in the representation. There's sparsity literature. I guess there's probably literature on sparsity about that. I wonder, how much of Mech Interp stuff is just we need to find the right things on the previous literature about, finding representations of things in vectors or something, or dividing vector or sparsity or whatever, and apply them. I guess the LEMs probably are going to increasingly be good at that.
Yeah. You mean apply some old methods in new contexts?
Yeah.
Yeah, I think that's true.
Like, it wouldn't surprise me if a lot of Mech Interp stuff is bottlenecked by, not being enough people that are there spreading some obscure subfield of mass and Mech Interp at the same time,
Yeah, like by the way, there is yeah. By the way, with the JSpace paper, physicists like to take higher order derivatives of everything. So kinda, I think there's lots of hidden math there as well. And like even with this one, like we're looking at the manifolds, and like I've seen that some less wrong people are starting to apply topology concepts and like calculating homologies or stuff like this. So like there's like topological data analysis of Mech Interp apparently emerging as well. We can read that as well. There's one less wrong post about that, which like counts like the different loops, different holes, and so on. So here you can see the different manifolds in the figure too. So if you wanna see like I don't know, you could. If something is in a circle, that's technically has one hole. So well, not really. It has to be a donut. So if some manifold is a donut, then it has one hole. So technically, you can classify that using topological methods, analysis, yeah, and stuff like this. I think there might be more math there.
Feel free to post ideas for things to read on the reading group channel. Not sure what we want to read for next week. We'll see.
Do you wanna check out the small less wrong post on topological data analysis?
We could read that one, unless there's probably also a lot of things. I think the problem is there are parts of the year where there's not a lot of things going on. We mostly read all papers, but at the same time, right here, like we are just after a big conference, so there's probably a lot of other things to read. So we'll see. But yeah, feel free to post it on the.
I think anything from Goodfire is good.
Yeah, Goodfire has also been. We've been reading a lot of Goodfire papers lately because they just keep posting a lot of stuff.
Posting a lot of banger. Well, some of them are slightly bait, but let's see if this one isn't bait.
Yeah. I wonder how much is this also like lately the LLMs are better, so they are accelerating the people posting this kind of thing.
They post on Twitter. They have some automated LLM agents set up that they made, like some custom harness or something, which apparently is better at Mech Interp than just using. Yeah, like if you like this tweet, for example, from them, you can see they have their own like
Kind of unrelated,
whatever that
but
is.
I'm curious if they'll, for the other, the Jacobian thing, they'll post how they found it. And
Oh, you mean
also,
the Jacobian conjecture?
yeah.
Yeah, that's completely missing. I think they have to use some math because like you cannot brute force that. So
I mean, yeah, I don't think it's brute force testing it, but I wonder, did they just tell Fable, find a counterexample to this, maybe with a lot of, don't make mistakes, be
yeah,
very, style prompts, or were they doing, did they do a lot of more math work?
yeah. I wish they released the prompt, the chain of thought or summary of the chain of thought, the output, and if any general math or specialized training was done, and if any general
Yeah,
or specialized learners was used.
OpenAI did do that for the defense conjecture. At
Yeah,
the
so
same
this is
time,
even more secretive than the
if they
OpenAI's
post
unit
it
distance.
later, I think it's funny if that it was just posted on a.
I, yeah, they didn't have to do that. I wonder if they. It makes it more funny. Oh god,
Now
the
the
tweet has 9
Wikipedia
million
page
views now.
has to cite Twitter.
Yeah. Okay, if anyone is out of loop, we're talking about this, which is from Anthropic employee.
But yeah, sorry for didn't start with that. Let's go back to the thing.
Yeah. I had a
Let's
bunch of thoughts about it that I see in the replies. Okay, let's continue.
We can talk about that one after the reading group.
Yes.
We introduced three. Yeah. So okay. So let's just go back. So to the sparsity. So they do something related with that structure. Oh, there's something about neuroscience here. Population geometry and manifolds. Also the manifolds in the brain. Single
Yeah,
network.
neural manifolds are also pretty
Yeah,
cool.
how much like yeah we need to apply more insight for neuroscience to make it better.
I'm sure that's the case a lot. Like they I think sparse coding itself was like originally in neuroscience. Well, in another field, so that's why it also came into Mech Interp. Partially. One of the reasons, one of the incentives.
Introduce three Block-Sparse Featurizers to use this principle. Okay, so these have this Block-Sparse Featurizers.
Minimum description length analysis.
I mean,
What do they
they're
mean
just
by
saying
that?
that is simpler.
I wonder if they do some formal. Well, yeah, counting the symbols. I don't know. Let's see.
With the largest nodes construction. And there's problems where like depends, how long a description is depends on the language and all that, but yeah.
Ooh, they have 4-dimensional concept. Well, I'm not
Oh,
surprised.
transport.
Yeah, that's true. Like all the visualizations we see are mostly like 1 or 3-dimensional. Like if you have some concept that's like 6-dimensional or something, that would be
They
insane
have
to visualize.
the BSF variants and they train them and compare with person encoders. More efficient descriptions activations. We'll see what they mean by more efficient. Yeah, okay, whatever. Discovering concept manifolds in vision novels. They find concept manifolds in vision novels. And you should also be able to, and seems like the other paper did, I don't know if the other paper is also Block-Sparse Featurizers, which is just another way of finding manifolds, but yeah. Also,
Discover novel manifolds including shadows and lighting in Dino V3. Dino V3, that's exactly what I was talking about. So they do look at exactly these vision transformers that do supervised. The way Dino is trained is interesting, by the way. Can I remember exactly? Yeah, okay, so the Dino V3 model, it's trained that you take a representation and, or you take some image, make it create some latent representation and compare it with a teacher, which also gets the image but slightly different. So like I don't know, you add noise, change colors, rotate it or something a bit. So this and the representations have to converge. So this way it's more robust because it tries to get as close as possible the augmented image representation to the original image representation. Seems to work apparently. Yeah, I think that's on a very, very high level. How Dino V3 is trained. Or Dino V1. I don't know about Dino V2 and Dino V3. They have some additional edits that I'm sure it's like very different at some point. But I think because it's called Dino that the idea will be similar.
yes. How does the featurization and some geometry enter expression? Okay, yeah, that makes sense. Some papers that cite will show that the natural featurizers consider this Block-Sparse method. Does anyone who already does anyone who already understand this part want to explain it, or should I try to figure it out?
Honestly, so their math part is really convoluted and confusing. Reading their overall descriptions pretty much explains what they're doing because they're using really complicated math here to explain concepts that they introduce and describe really simply in the contributions section. So
Okay, so I just go to. So which part do I go to then?
I think just skipping down to basically to 3 should work because all 3 methods that they do perform pretty much the same anyways. So
Okay. But how do the Block-Sparse Featurizers work, or do they explain that?
they do okay. So they have 2 methods. They use a shrink, basically a regularizer to try to. They use 2 different ones. The group lasso shrinks down the activations of blocks down towards 0 without any top K. The other one, which is their block projection, is a top K that looks at the L2 norm of each block and then does top K based on that. And then the only difference between the vanilla and the Grassmanian is that the Grassmanian has the encoder and decoder basically weight tied, and they do that using some orthogonalization thing from math, which they call, or which is called, where is that? Which is called stifle manifolds.
Eiffel manifolds. I heard that before, but I don't know what it is. I've been on this Wikipedia some time ago for some reason. Why? on the Wikipedia page of cycle manifold. Yeah, I don't remember at all.
I also happen to remember that steeple manifolds were used in geometric deep learning of sorts to learn symplectic geometry.
Interesting. Yeah, I'm not surprised because it's using groups. I see. Well, our groups are mentioned in the introduction in Wikipedia. And geometric deep learning is about group theory for others. Yeah.
But steeple manifolds had something to do with orthogonal matrices, is that correct?
I don't know. Orthogonal
pretty much,
K-frames.
Okay. So in theory, okay, so they have this Block-Sparse Featurizers. I'm not sure I understand yet how they work, but we'll see. So moving a control setting with yeah. So the measure manifolds. So here they are assuming that they like the same way that the sparse calls assume it's a sum of directions. They are assuming that the activations are a sum of low dimensional manifolds. Okay, that makes sense.
I like that.
With the manifolds, there's also like, some results and like ideas from previous machine learning.
I kind of have two questions about the math in the good fire papers. A, how much of it is generated by LMs? B, what is the background of good fire people? If they are physicists, mathematicians, computer scientists, statisticians, optimization theorists, whatever, pure or applied. I feel like it's a mix of everything.
Yeah, I do feel like sometimes there is some of the papers have been like some machine learning thing that you could have just figured out with machine learning, and then there is a lot of math trying to formalize it. It seems like there is some mathematician that wanted to make it very rigorous and very, try to add a lot of math. Sometimes it's maybe too much math for the thing on the paper. Or at least maybe someone who knows more math will be more interesting on it, but yeah, I don't know. Yeah, so
Additive mixture of manifolds. I think definition 1 is trying to formalize this notion of, well, it is trying to formalize this notion of additive mixture of manifolds. Abstract manifold, system dimension, immersive activation space. Through each manifold goes to some RD. With images.
okay.
If X is in the MI.
So they have this. Sorry, so they have this toy data, and it seems like the if you do this is the ground truth, you do the other methods, and it works. You do the sparse encoders, and it does these weird things that are not. Yeah, like here it seems like it's taking only like an arc of the thing, like some subsection of the thing. Whatever this is.
This looks like toy models, right? Ground truth. Those are toys.
Yeah, this is all toy models.
Toy examples.
They have some manifold, and then they try to find it with the different methods.
What makes it additive? Manifold superposition. How is it in superposition? So like the
Oh,
original model includes
so-
all these ground truths together.
They are assuming that I don't know on the toy model, but in general they assuming that the real activations are a sum of simple manifolds like this.
So in this example, do they like sum all these ground truth manifolds and then try to use the BSF to recover the
Mm,
different manifolds? Is that what they're trying to do? Return the manifolds faithfully.
yeah, seems like that's
Shutter and
what
collapse
it is,
them.
yeah. Yeah, recover excursion. Yeah, I mean, this is nice, but at the same time, like this is them using some toy data for the where their model, you know, they design to have the same assumptions as the model. The question is more if it works in real models. But
Yeah, they have that later.
they'll try that later.
This is supporting the union manifold representation hypothesis. This is literally that.
Yeah, that's so this is just a nice example of how it works. But on its own, if it was all that the paper says, it would be bullshit. But yeah, they do have real examples. Okay. So there is some
Activation X as a sparse sum of points drawn from few low-dimensional regions. That is very interesting.
also, what are these? So they kind of
They-
work are the same.
I
Is
think
one
this is
of
interesting
them
from the math.
is not this one, right? Yeah, I don't think so because it came up like around the same time, so it probably didn't have time to check.
Mhm. By the way, did you check just this image from the math section? I think which I posted. I
Yeah,
think it's also good.
activation X has part some of points down for low
Yeah.
division. Yeah, and so can you explain that image?
Yeah, so yeah, that the activation X is the activations that you measure. So, and that itself is composed by summing the different like MJ and MI from the different that are located in the different manifolds. So I don't know, it would be like a color manifold plus I don't know the amount of fur manifold. So if so, cat would be like I don't know, black cat would be like black color on the color manifold. That would be the MJ, and the on the furnace manifold, it would be not extremely furry, but just slightly furry. Well, mid furry. And that together sum into X and create cat. I guess that's my interpretation of this. I don't know if it's correct that properly. What does it mean, Minkowski, in this context? Is it like from Minkowski spacetime? Is it using the same math?
That's unique.
What is unique about Minkowski's cell? That
It's kind of like Cartesian product, but like with summation.
Okay. We work in the standard representation learning setting. For N, we write. They describe notation in the beginning, so let's see if I can group them off. I see usually when we read papers, Victor jumps to empirical results and I stay with the math. That's
Yeah.
interesting.
I mean, I think that's a nice. I mean, I think that's okay.
Yeah, I think that's good. It's like two subagents that then synthesize. Or, yeah.
Yeah, don't worry.
And others also look at other parts.
Yeah.
I think both are important. Yeah.
If people see something interesting on the paper they want to talk about, feel free to say it. Or like, or if there is some part of the paper we're looking at that you understand, maybe you can explain it. So yeah. Okay, so what else?
I've been looking at math all day last 3 days. This is another day. This is good. This is good life. Okay, let's continue.
If you enjoy it, then nice.
Yes. It's a good escape.
Okay. So anyway, there is some background noise on your voice.
For
I
me?
think. Yeah.
I think it's because I have too loud. Let me make it less loud.
Okay.
Okay, let's see if this will also have background noise.
Burni, Usagias, I was not looking at the math, but so maybe you can answer this question. Usagias,
Getting too distracted, I will go and look, yes. Understand why all the manifolds are B-dimension equation too. Okay, I didn't get there yet. Let's not get distracted by the Jacobian conjecture.
Okay, you were getting inside. Wait, come on.
Okay.
I mean, understandable, but yeah, we can talk more about that one after the intro.
Yes.
But let's try to look into the paper first.
Yes. I need to somehow block all different Discord servers. No, I will. Okay, let's continue. So, you write N. I'm a bit confused. Like in the exactly first notation, why are they using n in small n in square brackets as a synonym for the natural numbers? Why not just use the natural number symbol? Why are they inventing an equivalent?
Mission by explain.
What?
Okay, let's look at this.
Okay, this is what I'm confused about. Well, let's see. Oh, because you specify the number. No, it's not the same thing. No, I'm so dumb. It's a completely different thing. Okay.
Okay.
Because it's finite. It is not the whole natural numbers. It's only a small subset of natural numbers. Okay.
Wait, yeah, I can test that. Yeah, so they've been studying the degree Block-Sparse Featurizers activations. But it's explained. For stable reconstruction to be usefully faithful. Okay. We mentioned the quantity presentations continue improvement of the grade. I wonder if for different tasks that mission is different though. Like it's maybe not the same. I know that the different models, how much you quantize it. I guess it's quantizing the representation or not quantizing the. Wait. I'm a bit confused by that.
Where quantize exactly by it?
For the since you are talking about the B there, like the dimension, is that like is there a trade or what are the trade-offs for the the dimensions of the blocks? Is it just if you increase the number of blocks is always better but it's more compute, or is it you want the smaller ones because you kind of want to divide the activations in simple in simple representations or something?
Oh yeah, I see the B. Are you talking about the same B? Right now I found the B. And
they're talking about the one in equation 2, yeah.
For assay coefficient Z that belong to R BG to G blocks. They use B here without any defining. I assume it's a natural number. There's a G. ZG belongs to RB. Okay. Okay, I see.
Yeah. Wait, so I have another question. Okay.
So I guess
Maybe it's explained better elsewhere, right? But here they say that okay, so they want to establish the noise floor at which quantized representation can perform some task. Like, but so bar for reconstruction to be faithful. What do they mean here by gradually quantizing the representations from Dino? Do they mean just gradually quantizing the activations of the model? Or are they or do they mean something else?
I guess you can quantize in Dino, but also in assays, I guess. I don't know. But I'm seeing the Bino. So you have activations X that live in RD. And then assay coefficients live in ZR to BG, where G are the different blocks that you partition into, from Z1 to ZG. So each Z in this block belongs to RB. So I guess RB is how many dimensions you have in assay for each activation. Is that what B is? Or what's your understanding of B?
If you look at the chat, they say something already that that both Ryan and they say that it's a hyperparameter that you can set that is the dimension of the
Yeah.
blocks. So
Like if it's so is it just the amount size of the block? Yes. And is each of the blocks SAE coefficients? SAE latents? Because they talk about that for a code, for example, SAE coefficients for Z that are partitioned into G blocks. In each block you have the G, which belongs to RB. So I would assume that's, for example, SAE coefficients. Okay. In SAB1. Okay. Oh, okay. So that makes sense.
actually, what's the difference between a Block-Sparse Featurizer with B equals 1 and a sparse encoder?
It's more general, I think.
No, I mean,
That
but
you
when
can
you set the B to 1, like what's the
like for a code, like B, like that's broadly any code. So SA is one type, one special case of a code. SA coefficients. Oh right, I see. SA coefficients. Okay. So basically, in the SA example, you change the SAE by, instead of the latent being one row number, you numbers you or something like that. Oh, I should I very much want to use CGPT and close to try, but I want to use my brain.
I wonder if that's like, I mean, maybe that's true, but maybe if you use it on like bigger models, you find that have been trained a lot more. Maybe you find bigger manifold with more dimensions or something. But maybe it's all, you know, a lot of simpler manifolds with less with at most 4 dimensions. I would be curious if you run something like that and you find something with B a lot or something. You if some case where you need to increase B a lot, what that concept or whatever it seems to be.
So top is indexes where the blocks are not zero, where the coefficient, where the code units are not zero. Okay. The whole block is not zero. All right. Oh, so there is already some paper talking about activation being composed of a sparse set of manifolds.
I mean, there were a lot of papers saying that, but the not. This is more, a method to find them, right?
Yeah, but like that you just don't look for one manifold, but a set of them. Or some. Well, it makes sense because of superposition, I guess.
I mean, that's necessarily the case. I mean, we already knew that there was more than, it has to be more than one, because you know that I don't know, if the dates of the week or whatever are circle, and some, I don't know, years are other different manifold or whatever, you know that some centers that includes both constants has to have more than one manifold.
Yeah, you're right. That's true.
And also, like, if you think of the sparse recorders, there are a big superposition of a lot of things, a lot of directions.
Yeah. Yeah. I think I'm just happy to see it formalized as well. Okay. Check my thoughts. So N1 to M to N abstract manifolds. There is a difference between a manifold and an abstract manifold. Manifold in the context of an abstract space. Alright, sure. So the abstract space here is latent space. Or yeah, basically something like that.
Okay,
Then
so
choose
maybe let's comparison principle. So you
Manifold itself is defined using topology, using neighborhoods and stuff like this. I need to remind myself how exactly that's defined.
I was trying to look at the empirical stuff where you look at the math, but then I get distracted by you looking at the math. So, so maybe that's a problem with the. Doesn't matter.
I sometimes have it the other way around.
Yeah. That's,
Yeah.
the comparison is confidence.
By the way, Bernie, just a quick heads up for you. You know, topology and geometry on manifolds is one of those areas which has a layer of symbolic abstraction, as we talked a while ago about finite versus, constructivist versus symbolic abstraction. And so that's the area where the difference between the symbolic representation and the computational aspect is relatively large. So that's why it's not strange that it's not immediately obvious what a neighborhood is and how that's defined, and all kinds of
I went through,
continuity
yeah.
issues.
It's more like that I went through it a long time ago and I don't exactly remember it. But I don't think it's exactly needed here. But yeah,
Right. Yeah. I'm sorry, guys. I just got home, so I just started watching your screen. Please don't mind me.
yeah, all good. It's a good comment. I don't have any problem with infinity myself, by the way. I can switch my brain to infinitist mathematics and then to constructivist as I need. I think. Okay. If that's what you meant, I'm not sure. Yeah. With dimensions, let's see. Someone interviewing someone was saying like when I talk to someone, I am on his side or something like this, which I think tries to express this idea of trying to steal man the other side as much as possible by becoming his perspective. I think I'm also trying to do that with different schools of thought in math. Yeah. Okay. Thoughts with Team N1.
Come on, can decide that, but okay. 6 blocks from okay, so how these blocks? Oh, cool. B equals 1 code. We'll set the concept. Okay, here's the thing I was wondering about. Learning in the block dimension, there is one constant on Earth. The residual strings, where the code turns global since the coordinates must be transmitted per active block. Create a distortion of that.
Okay, I'm a bit confused about the figure though.
Which one?
That I posted before. The figure 2 that I posted before, because in the figure they have the points live on the MI, but the MI is when you take the low dimensional manifold, then you cast it to the higher dimensional activation space, RD.
Yeah, like the actual activations are on the
Okay, actually, it
higher
makes sense, yeah.
dimensional space.
Yeah, okay, this makes sense.
More compared description activations. Okay.
It's a bit weird because you. Yeah, okay.
I wonder if the other paper was simpler. No, that's also.
Yeah, I think it's a good
It was shorter, but
visualization.
yeah. Better
I
precision
love
one.
it to see it verbalized. Okay. So what empirical results did you found so far that are you're looking at the Dino V3 now?
I'm getting better started, to be honest.
How will they flow
A lot of
manifold?
they tried a bunch of metrics and seems better on those metrics. Some of them are like trying to quantize it and see if it has the same performance or whatever, and then and different reconstructions or whatever. But yeah, I'm not sure I understand all of them anyway.
Quantizing the original model then, Dino V3, just like you quantize LMs.
Yeah, I think so. I was a bit confused by that, but I think it's that to try to see what like how precise a reconstruction needs to be to be good in that, and they use quantization for that. Not completely sure I understand like how you.
Grassmanian.
Yeah, I guess that they're using it the quantization as an estimation of how much precision you need with the reconstruction to like they are quantizing and testing on some downstream tasks. So they're testing like how much precision you need to for the model to be good, and they I am slightly thinking of that. I don't know why they don't just directly test the model with the featurizer thing on the downstream task, like with the blocks, like you can do with the spot encoder reconstruction.
I'm noticing Grassmanian isn't Grassmanian. Is it the same Grassmanian used for amplitude-hedron? Which is one way to make, I think, in physics the standard model more simpler or something. I don't know. I wouldn't be surprised. Oh yeah, it is. But I'm not sure if it's the same Grassmannian. Okay, I have to check more because the mathematician Grassmannian, Grassmann found a lot of things. Probably. Hermann Grassmann, yeah. Yeah, there's a lot of things named after him. Okay. Yeah. Yeah, I'm not sure if I exactly caught what if you were asking something, Victor.
Don't worry.
The atom. I like. Equation X follows the additive mixture of my thoughts model if X. Bit confused. They suddenly use the letter S and M. They don't exactly define it. I guess you can infer it. Let's. I guess S is the number of manifolds. Oh yeah,
anyway,
it's M is
maybe
the number of
this
manifolds.
doesn't make sense for some reason I don't understand because I don't really, it's not the math. But could you just, since you have on the J-Lens paper, could you, like they were using decomposing things in directions in the, directions in the from the Jacobian? Could you somehow do the same but with blocks?
Well, you use activations here, so you can always take the Jacobian directions.
Yeah, no,
Of
but
the
I mean,
equations. Yeah, I'm not sure if I exactly.
I'm not sure
Since I
this
don't
makes
yet.
sense.
Well, well, more generally, the general idea I got from you is that Usha just says it's a good idea. So maybe he got it.
Yeah, like, I just have a big idea of the J-Lens but manifolds, but I don't know.
Yeah, I was
How
thinking about that as
just
well.
to translate the math from this to this, but it seems like it might be, but I don't feel like I understand it enough to be able to say for sure that there is not some subtle detail where actually, there you are the Jacobian and you cannot add because whatever math reason, but
Yeah.
uh,
Like first, I would try just normal SAEs with the JLens. Then I would try this manifold thing. Combine it together.
ALS is already giving you directions, is the thing. And they are already doing some sparsity thing. On the aliens paper, I didn't get much to it when we were reading the paper because there was a lot of paper and that was kind of complicated. Because they have a lot of vectors for all of the tokens, and so for some of the experiments they have to decompose it in a smaller subset. So they have some sparsity thing, but that was still, getting directions. But yeah, I guess the Jacobian is directions because it's like that's the output of the Jacobian. But is there something like
Well,
that? But
output is a yeah. Well, in the JLens, the output are the tokens probabilities, or Jacobian itself. The output is the derivatives, the matrix of the derivatives of partial derivatives, or so. Okay, I still don't get fully how they do the blocks here, so I have to finish the math to see that. But like, they take activations here, and then they decompose them into those manifolds. I guess you could do that. Maybe you could like pass the different the thing that you sum together to get the manifolds that you sum together to get the original activation. I guess you could just pass the activations corresponding to just the different manifolds through the logit lens or JLens, and you could get some tokens, possibly. I don't know. I have to check exactly how they play with little blocks. I'm still deciphering stuff before that. Okay. I have to first feed as well before that we're kind of getting math singularity before any other types of singularity when you think about it.
yeah, maybe I'll ask Claude when I have grades back. Because I
You can
spend
partition
them
Jacobian matrix into blocks. Yeah.
or do some equivalent thing. Yeah, that could work maybe. I don't feel like I have enough good understanding in my head to be able to tell if things like that make sense or not. I'll probably need to spend more time thinking about this. At the same time, I think I was also slightly when the sports encoder thing came out. I feel like since then a lot of more. I've been reading a lot of more papers of them. I think I understand a lot of sports encoders now. Maybe I'll if this kind of thing becomes popular, I'll slowly understand a lot more about all of the math of the Block-Sparse Featurizers. So maybe I should have read the paper before the reading group. But I keep saying I'm going to do that, and then in practice I end up just reading it here anyway. So
You can try to read them together before the reading group as well as another option.
we could try that. I don't know how much people, even them, will still prefer we go through it anyway. But yeah, it will probably make us spend less time being confused.
On the other hand, when we're all confused here together with others, that
Yeah,
makes
I
it
think
slightly faster.
that also is nice. Like it can help if there is more people to try to help figure it out at the same time.
Yeah.
I don't know what format will be better. by default we will be doing the all people being confused one, especially because the other thing will require everyone to have read the paper beforehand, and especially with me not remembering to put not deciding the papers until it's very close to the reading group. It becomes harder. But yeah. There is also the thing, it's been a while. I need to go back to try inviting the authors of papers. Because that's also
Actually, I
nice.
think this paper is good. The math is. Someone said that it's convoluted. So far, when I'm going through the beginning, I'm too slow. I feel like it's good because they literally define everything as far as I know so far. Like they don't assume you. The only prerequisite. Well, I guess you have to know what manifold is. They don't define manifold. I don't know.
I don't think they could explain. You can explain things with less math. At the same time, I understand why you like it. You know.
Like every time, like when there's. I was talking about to someone who was, by the way, I invited him here. He maybe will come. He told me he took before the Jalen's paper that he was doing some similar things, and apparently he take higher order derivatives, not only first order, in Jacobian, to also do some interpretability. And we were talking about how we're reading the Anthropic and other papers, and we both of us instantly skipped to the math and most of the time. So, and he comes from physics background. I hope I will get him here some other day. I will tell him explicitly, hey, do you want to come next time or something?
Yeah. Okay.
Yeah.
I mean,
Maybe
Yugi, Bernie? Yugi?
I I don't think his name is Yugi, or is it? Yeah, Yugi. It's Yugi. I was talking about Yugi. Yeah.
Yeah.
He's very nice. I don't know,
Yeah,
but I don't know
yeah.
if I will believe what he said about the higher order derivatives until I say it. That
Okay.
is, but I think it's very likely that taking higher order derivatives will lead to some new interpretability stuff. So
Yeah.
yeah,
Remember the second order partial derivative and sums of, are very much related to harmonic analysis, right? So
yeah,
function
that would
that,
make sense to me.
right? So periodic, wave-like stuff.
Yeah, if like, I'm not surprised there's a connection there. Like, since if the activations causally change in some periodic manner, then you can find all sorts of on first order or higher order change and so on.
Yeah, and if
And I'm not
these
surprised that you can
manifolds,
find some like patterns there like this.
yes, and I think the I'm not sure, but the manifold theory states that, or manifold hypothesis, that we're dealing with smooth manifolds, and that means that the degree of your derivative, or sorry, the order, if you differentiate once, twice, maybe 3 times, 4 times, you're already at 0. So it's not going to be an infinitely differentiable, right? So you can only go up to order. At least that's why I think if it's smooth, what it means,
Yeah.
if you keep differentiating and you still have obtained non-zero answer, then it means you have, you're dealing with derivatives of high order, basically, right? So that means data that changes very sharply, which is, I think, these manifolds are supposed to, if you take a neighborhood and you look at the smoothness and it's locally linear like Cartesian, and you go from one point to the other. I don't think, I'm not sure what the constraints are, how non-smooth, the jumps can be relative to. This is kind of what I'm just trying to dig into, like this part of things,
Riemann locally Euclidean, which I
What
guess
did
you
I
could say
say?
linear.
You look at the
You
Cartesian.
said locally linear.
If you look at a small piece, Yeah. So that's
Yeah, that makes
because a
sense.
lot of this stuff, all this, feature extraction and geometric structure, in the end, it lives as linear algebra, representations in the end. But the interpretation is that then it's an approximation of a curved, geometric space. But actually, it's
Yeah,
just linear spaces with certain conditions. That's another way to look at it, basically, kind of. But then you don't have the geometric picture in mind, which can be very handy if you're especially thinking about gradients and other, geometrically
yeah,
visual.
from the approximation lens. If you, I think physicists like to joke that they like to take Taylor approximation of everything. So you just take the first derivative and all the higher order derivatives in this approximation you just throw away.
Right.
When you're Taylor approximation is cool. I was thinking the J-lens that technically that seems to come from the Taylor approximation, I think, as well.
Right.
Since you're doing this local linear approximation using the Jacobian, if I understand it correctly, hopefully. Yeah.
I don't want to divert from the topic of this paper, but I was reading a little bit the abstract of it. And so they're thinking, instead of directions, they're thinking about these blocks, sparse blocks that encode
Well,
features or
okay.
something like that.
More broadly, when you look at the activations and when a lot of people assume that it's that the different representations are just like straight directions. Well, and these manifolds are more like assuming that actual activations they live on some geometrical shapes like manifolds. So like you can go in a circle when you have a day of a week that goes in a circle. So that's a
Right.
circle. So that's a manifold. So this paper is about finding these manifolds in unsupervised way, which is the new
Unsupervised,
thing.
right. Interesting.
Yeah.
Interesting. Yeah, thank you for that explanation. That's exactly what I wanted to hear. I follow most of that, of course, not the details, but kind of.
Yeah. Okay, I'm gonna try to continue deciphering the math. Do you find some empiric evidence that's interesting, Victor? Did you find some interesting empiric evidence?
I keep getting started. Uh, I mean, not yet. Continue with your math stuff. I'll try. I was also asking some questions to Claude on my screen.
Yeah. Also, if you want, I can try to explain to you the definition one. What's
Sure,
happening
you
in the
can do
equation
that.
as well. After I'll decipher one last part of it, though.
Okay.
There's
To that, meanwhile, I'm going to go a bit down and try to read at least some of things. Feature precision traitors locations. This multiple leaf. Have a score from for it. Okay, that's nice. I was thinking. So, Ryan was saying he's doing, some experiments with the Block-Sparse Featurizers, and something that could be interesting is there was some paper that they were talking about in machine learning street talk that was claiming that, I don't know, Bunny knows which one I mean. Maybe he can
fracture
post.
entangled representation hypothesis.
Yeah, that thing that claimed that that I thought was using some bad methods to claim that the representations on some learn model were bad and their method was better, and I suspect that on the that the representations there might actually be some manifolds. So I wonder what happens if you could try applying the Block-Sparse Featurizers to if they have the code somewhere or something, the models on that, and show that they are wrong.
That's interesting question, possibly. Also, like the model
Is
that
it
they
what
have
you just
there.
posted?
Yeah, the one
it
that
was
Murni
also
posted.
like the model that they have there is like a model that generates an image. Is very specialized subset of images. And so that's one thing. That's why there's not really possible generalization across vast amount of images. B, it's a very, very simple architecture. I think they use vanilla as GD as well, so that's another issue. They don't use ADMW or something like that. And so they don't use any like tricks like so in ADMW for grokking you need like the weight decay, or you don't need it, but it's better. Normalization like weight norm also helps with like generalization and so on.
Yeah, I think it's
Well, you also
possible.
need diverse data for generalization. So they have very old architecture, very old like very old optimizer you could say, and very small data, and you cannot make such general statements, I think, just from this
Yeah,
paper.
I think, but I think
That is my
even
take.
that it wouldn't. Maybe it turns out it's useless because their model is just too bad and it doesn't have good representations. But I think their method for checking the representations is just, going through. They move through activation space in the naive way. They just take the activations and move through them. And if maybe there is just some nice manifold where the example where with the schools or whatever it changes in more sensical way if you find the right manifolds.
Yeah, maybe.
It could also be that's not the case, but maybe that's a simple experiment that can be done. I could also try running it myself later with Claude's help or something.
Yeah. I think that's possible.
And this isn't hard. I guess maybe this is probably just a very bad paper, and the correct thing to do is just not pay much
Yeah,
attention
it
to it.
is.
But at the same
I'm
time,
not sure.
the machine learning street talk people were paying attention to it because I think they interviewed the people anyway. So
Yeah,
sorry,
like
we were doing something.
at least recently, Tim from Machine Street Talk seems like he's more.
He's getting manifold
How do you say?
peeled by the good fire people.
I guess that's part of it. Yeah.
Yeah, I don't know. Uh,
Also, he was more like I personally. Okay, so there's this question if okay, maybe we can talk about later.
yeah,
Whatever.
let's go back to the paper.
This would detour for ages. Okay, yeah.
The natural. Yeah, okay. I should also be back to here. I was just getting started thinking about this about that thing and that paper on the. Yeah, and I okay. So I'm also interested in if people apply this kind of thing to describe Block-Sparse Featurizers or whatever other methods people find to find manifolds. Can you recover all of the ones that we already knew about? Like the math thing, the sentence length one, the days of the week, all of the things that we knew that they follow some simple manifold with a few dimensions.
Yeah. Recover
If you
stuff.
just apply to LLM some method like this, what do you find? Also,
Can you recover numbers in a helix? I think would be one good experiment. Yeah. Also, yeah. Why do they call Minkowski sum? That's one more. Read the definition again.
Also, Usagi says that the question 4 is the crux of the paper.
Oh. Means Kafka Sam. Okay, I see. You mean what you meant with the productive addition. It's just if this is satisfied, right?
Okay, so
Difference. Like, you know, sometimes it feels like it uses a lot of unnecessary math, but there is a reason sometimes, because you unlock a lot of theorems from math, then you can start proving a lot of things because of that, and B, it's more general, so you can apply it across domains. That's the power of math, I think, in big part. Yeah. Okay. Do you wanna see the definition one? What they mean there?
Okay, you can explain it. Yeah, explain definition 1, Burnie.
Yeah, so they try to formalize the concept that each activation is sum of the different points on the different submanifolds or different manifolds. So they first define the abstract manifold that are which are the N1 to Nm, which have lower dimension than the whole activation space. So that makes them less dimensional. That's the dim N1 is smaller than D. So I don't know why they use smaller. Why they use 2 is smaller than their 2 inequalities. I'll check. Yeah. And they also define this map that you can go through from the, I think this is gamma. So for each manifold, so I, so you have gamma I, so which is for each manifold there is this gamma function that maps from the low dimensional space Ni to the activation space, which lives in RD. So the real numbers, d-dimensional real numbers, which is this, activation vector. And there's also so you can so you have this image that equivalent to they also show it that they also label the output of this function as mi. So that's when you take the manifold from the low dimension space to the activation space. And that itself lives as a subset of the activation space. So each manifold is this subset of the activation space. When you project them to the activation space. So an activation in this activation space is like this additive mixture of manifolds if, and then they have this definition there, if the X is the sum of the different different points on the different manifolds in the activation space. So if you can, and the different eyes live in the different subset of the different manifolds.
Remember, the paper is this one.
So I'm not sure. Yeah. So I'm not sure if you got exactly. Do you see what I mean by the definition now, or do I assume too much things that one has to know?
I was kind of distracted. Sorry.
Okay. Yeah. Well, yeah. It's mathematically formalizing the that you sum the different manifolds.
Okay, is
Points
that
from the
saying
manifolds and get the
that you
activation.
have the manifolds and the manifolds lay on some point in the space of the activations?
That you can that the abstract manifolds themselves live in the smaller dimensional manifold, and you can project them to this high dimensional space of activations. And that then when you sum together the different points from the different that corresponds to the activations of the different manifolds, you get the original activation.
What is a block
the
exactly,
sum.
by the way?
Okay, there's no blocks here yet.
You haven't gotten to that.
Yeah, this is just the additive mixture of manifolds.
Yeah.
I just wanted to understand every single symbol here and every single word here. So now
Okay.
I'm satisfied. I'm gonna continue. Yeah.
Like, am I correct that each block correspond to some manifold?
That would make sense. Let me see. Here. No, there's some more math. Okay, they start talking about blocks. Also, why do they use the double? This is weird. Why do they have like double inequality here?
Some people writing. Okay, yeah. Okay.
Yeah, and
So it's okay on the blocks. They are on. Okay. Blocks and the
block
space
is
of
the
each
ambient
manifold.
space of each manifold.
Right.
Right. Isn't it same for every
but
manifold? Aren't they all living in activation space?
No, but
As the ambient
I
space?
think you can select a subset of activation space that has the full thing, right?
Okay.
Maybe that's what it is. But how you get the actual manifold from the from the ambient space?
Okay, it's much less than. Okay, so I'm gonna continue.
And Ryan just left because he probably knows, but that's bad. Never mind. There's the Pearce. Okay. Yeah. Okay. So the insertion B1 is the one from the original Mech Interp paper, right? Like this still thing with Curt
Yeah.
Yeah.
That is
Okay.
an ancient result.
And they had a bunch. This is a nice result. So this is a nice empirical result. So they had a bunch of curve detectors that seem like a mess on the original thing, but seems like turns out they seem to be a nice manifold. And the Sparsity encoder styled the thing.
Can you ask or say it again?
They talk about how people have used Sparsity encoders
Oh, yeah.
more lately.
I think
But the Sparsity encoder styled the manifold, but they didn't completely tile it. But if you actually do the
Yeah, this is also what I described in the geometry of line breaking paper, this duality that SA features style the manifold.
I mean, we read a Woodfire paper about that, like more in mass detail, if you remember.
Oh yeah. Yeah,
We
they
were also
also
talking about the ambient space of the
yeah.
manifold, how the different ways you could dial it, and
Yeah.
how they probably correspond to some of the problems with sparse encoders. I feel it's a block of 16 dimensions. That's how I used to then. Nice, another spiral.
Okay. What spiral is this?
This is from the Inception one.
Oh yeah.
Curve detectors.
Oh, I think the new thing here is that they also find some higher order harmonics. Oh yeah.
Mm-hmm.
Decomposed. More than the orientation of circle, its leading components are higher order Fourier modes. I think that's the new thing that they find. I remember that from the tweet.
Yeah. It's easier to see on image models, but can we just, even for image models, can we just take this PFS and run them on a lot of images and see what
Like
the different.
Yeah, I'm
I
surprised
guess
they did it on
Ryan
vision.
was
What-
finding that it was harder than it seemed, but maybe at the same time he was looking at things like count or whatever that might not be. But yeah, maybe well represented in the model.
Geometric assumption. Block-Sparse Featurizers.
Oh, nice. The cover colors track existing illumination consistently across objects.
My neighbor started doing.
Hmm?
I don't know if you hear it, but my neighbor started doing wood. So I will close my.
Oh no, it's Discord is blocking that. There was
Really
noise
blocking
before,
it?
but yeah, because like the problem is when it's voices.
Oh, I will close my window anyway. They used some Bayesian treatment of the group sparse penalty, so they have some group sparse penalty. Okay. Each factor occupies two
Very
dimensions.
well, I think I saw. Very diffusion models. Nice. Yeah, this is the pattern interesting on the very nice numbers from math. I don't completely understand, but I kind of want to see cool images. Shiny.
Tiny result.
Yeah. I do think the math
Like
thing
it's
is
good
probably
that it's actually applied in practice. A lot of deep learning
Yeah, I
theory
mean,
is
I do
just
think
math, no practice. So
that's
I
true.
like
I do
Mech
think it's
Interp
good that
also,
they
but
put math. I was half joking about the thing. It is easier
yeah.
to understand the concrete examples. At the same time, it's also good to know that the math is not, wrong or misleading way. It's easier to see that it's, actually useful for something that's harder to fake.
Yeah, the math looks legit.
Oh, nice. It does. They say it's not improved, but it seems like there is something here where some direction is. You know, like on the coffee example, it seems like it's like on this direction the coffee is more like dark and less they don't have shapes on them. And yeah, and here on the hats kind of becomes smaller. It seems like there's some geometry of hats that is coded in both directions. Something I will worry about is how much. Oh, wait, I think. Yeah, never mind. Something I would be worried about this kind of thing is how much is the thing that you will find coffee there because you found the coffee manifold, or because you are picking points that are close and points that are close are coffee. You will want to see things that are close to the current point, the point that generate this, but like spirit a bit of the manifold or something, and see that the moment you get outside the manifold, it starts getting worse, plus or something like that.
No, I was reading math. I wasn't paying much attention. Do you wanna say it again?
Oh, sorry. I was thinking of like, okay, so how much is the like so for example, if you just do steering, how much is the fact that you get images from for coffee because you got the correct manifold for coffee, or because you are steering around the same part of the space? And if you like, I would want to see things like if you go close but slightly off the manifold, it starts getting worse much faster than if you go around the manifold and things like that.
I would
That
expect
looks
that
less
going
like
off
coffee.
manifold would. Yeah, that's a good point.
I kind of, I guess
Like
I
going in
what I
some
want to say
orthogonal dimension direction or something.
to see, like, it would be nice if there's someone publishes some either they put in Neuropedia or something, or some web where you can take a train Block-Sparse Featurizer on some image model or whatever, and play around with the blocks the same way you can
Yeah,
do
yeah.
that with sparse encoders.
Well, someone posted in the chat that they were experimenting, so
Yeah, but
I'm not sure how he
yeah,
got it.
Ryan said that, but he left a bit ago.
There's a GitHub for this repo, I think, for this
Yeah,
paper, so you can use that.
yeah, I guess I
I
can
guess you have
download it
to just
myself,
scaffold it
but
yourself.
maybe
No,
I should
I don't think it should
when
be
I
hard.
have Claude grades back on Thursday. I could try getting Claude to make a interactive page and post it somewhere.
That's a good point. Did someone do that? No. Yeah,
I
I
don't
would do
know.
that.
Maybe by
I
then
mean, that should be super
someone
easy.
will post it.
I mean, it would be nice to have this and also like combine it with essays and others. So you
Yeah,
could
you can
just
have a
pick
thing where you
essay,
have
pick,
this
pick, pick.
and have this, and you can compare how well they do, like visually.
I kind of wanna do the page as well
Okay.
to do ablation.
I mean, feel free. I will be okay with. We could look at into that together one of these days with this week later. Especially because then I also get to use your infinite, not infinite, but cloth crates and or LGBT crates. Like now I
You want, I
speedrun
can do it.
spending Fable crates while I still had them, so I already ran out for this week. Remember,
Hey,
were
Rambert.
you going to say something? If you are
Also,
very confused, I can. This paper is basically like sparse encoders, but with manifolds from Woodfire.
Yeah, the Matryoshka sum between manifolds is each of the features have their own unique manifolds. Is that what it's saying? Convex
No,
or
it's
manifold?
saying that the activations are as like here is like sparse encoder, but a feature is a manifold, yeah. And the activations are represented as a sum of manifolds, I think.
oh, so that's what the blocks are. Each block is
I
a
don't
manifold.
know.
Okay?
Because
Letters
I
M.
Usagi
I don't
says that
know.
the blocks are the ambient space of the manifold. I think Usagi is still confused about that. So it's
I
apparently
thi-
on part 4. So you'll get to that part and explain it to me. But
I think it should be.
M seems to be the number of manifolds, and they're summing across the manifolds to get the activation. But I wonder how they found all those manifolds.
yeah. So
If you
Well,
look at
my
token one,
understanding
the
is they have
general
blocks, and the blocks somehow each block corresponds to a manifold in some way.
Yeah,
And
they
they are
might be
training
opposed.
them like sparse encoders with reconstruction. I think.
Yeah, so are they training assuming N manifolds, or are they just finding these N manifolds and they just found it was 5?
So I
If
think
you look
it's
at
like
2.1, do they give an assumption for the number of manifolds, or is it like some sort of
yeah, I
unsupervised
think that's
manifold?
a hyperparameter.
I
The
think
number
it's
of
just
manifolds.
like sparse encoders
I think it's like
sparsity
set. I
penalty.
think it's set. Like so far, my gut instinct says is like thinks it's like set. Like they say like it's going to be 5 manifolds to
Like
make this
block is a linear subspace that contains the manifold.
So as I understand it from the things I read, I think the way it works is just like sparse encoders and it has a sparsity penalty. Like it trains the model it trains them in the less blocks you use to summarize some activations the better. And that's how it works. So there is no fixed number of blocks, I think. Or depends on some hyperparameter of how much. Yeah.
So the BSF learns the b-dimensional linear subspace represented by the basis. What is inferred from the collection of contributions MG. The manifold explicitly assumes that each manifold lies in a low-dimensional linear subspace. That's technically an inductive bias, you could say. So when the concept is curve orientation, so the block is the entire two-dimensional plane, and the manifold is the circle traced inside that plane. So that's why it's ambient. Okay, so it's subspace. Yeah. It points inside that plane.
Also,
So
Sony
it
posted a
learns
link
the
like
different
code explaining.
subspaces.
Okay, so Vanilla Gasmania is K blocks. Okay, so it's more complicated how they do it. The code is never to respond, just press simulation. Okay, yeah, so they use different methods for the 3 BFS, and it's not sadly like the sparse, like it's just not just sparsity penalty. They on the BFS are more like the Grassmanian and the vanilla and Grassmanian are more like the top K, where you only have a certain amount of blocks that you use.
So they are not baiting us. It is actually essays, but for manifolds.
Why?
They are not baiting us. I said, since
Ah.
it's literally essays for manifolds. You could say.
Yeah, I don't completely understand the part with the blocks yet of how you get from a block that seems to be a set of dimensions, like a block seems to be a set of dimensions. Like if you imagine like the spectrum coders, you have an activation squad are an arrow, right? That's one direction. Instead, the blocks are like a subspace with more dimensions. You could imagine like a 2D slice or a 3D slice, or something. But I don't know how you get from that to manifolds, because the manifolds are so can be inside that, but are actually only some parts of it. Okay.
Is the concept present? Is the block norm of the block?
Blocks are not proposed here as a universal atom representation, but as an example of what's possible if factories is matched to the model representation in mental plane. When the geometry is hierarchic, a temporal overlap in composition, the match objects represents accordingly. Okay. Decompose the representation with atomic units, but to infer what atomic units the representative must be.
I wanna check
is
if it learns a line, is it equivalent to essays?
Apparently, Claude told me that they have something about that with its b equals 1. It's almost an SAE, but it's slightly different for some reason. But I don't know if Claude was hallucinating that. It claims that it was somewhere on the blog post or something. Or maybe, yeah, maybe it was just hallucinating.
Like, it would make sense to me, because functionally, I think it's true. So if the block has width,
Train to minimize reconstruction error, yeah.
so even if you have a block with width b bigger than 1, across all inputs, its code always lies in one fixed vector.
They're basically saying that you also the discussion about future world. They're basically saying that you need to that we need to, like interpretability needs to find the correct atoms for like instead of blocks, find whatever from model what the best units of the representations are.
Either if it learns just a single line that makes it function equivalent to a SAE, and if you set B to 1, that should make it
Okay, that makes
architecturally
more sense.
equivalent to a SAE.
Bernie, we've been the ship yet again. So the method just decomposes the model in blocks, right? But it does. They find the manifolds later doing PCA on the blocks, right? That's what Usha is saying. But they don't find the manifolds automatically yet.
How do they get the manifold from it? By doing PCA on the blocks, you mean?
Yeah.
I mean, you can still do that in unsupervised way, no? So you still have manifold in unsupervised way, no?
Yes. Yeah, I guess it's easier to do that if you have some blocks and try to
learn the block subspace, collect the block contributions, form a point cloud.
Also, I guess that goes to this other paper that we were doing was similar. That is, subspace aware. It's more clear about that. This is subspace aware autoencoders. So, like, instead of finding manifolds, we're actually like you are dividing the modeling subspaces. I guess is the thing. Which is not the same as finding manifolds.
Dataset condition point cloud analysis inside a learned subspace is how you get the manifolds. I mean, you get the subspaces, you do PCA, that can be done in an unsupervised way. I guess in an unsupervised way, you can do also the spline fitting to fit the manifolds. And that makes it fully unsupervised now.
I feel I feel like that has problems though. I don't know if that scales to the because you can you do the spline fitting for like I think you need some. I don't know. I don't think you can do the spline fitting. You just have a bunch of. I think you can do it if you have a bunch of examples of. I don't know if you can fit the splines into just a random activation. I don't know. Yeah. I suspect that applying Block-Sparse directly to the language or video. Okay, so they're saying this wouldn't work well in language or video. And Yeah.
Orthonormal frame. ST. ST.
In any case, I think this line on research of people trying to find like higher dimensional equivalents to sparse encoders is nice. I don't know if this version with blocks and whatever will be the one that actually ends up working better. But it's nice and it has some cool results like the
Learns by
like
reconstructing each
the
activation with a
section
small
B1.
number of active blocks.
But I feel like when we get the cool final, the actually good version that the composer thinks better, will have a paper with a lot more examples.
So you take. So suppose the hidden data contains two independent actors.
Where are you, by the way?
I got stuck that they started talking about the Stiefel manifolds, and I am not. I would have to look more what exactly that is in this context. So I'm now thinking of going through some concrete example without this extra math on top of it. Let's see how the data transforms to get the manifolds. Set of n times k matrices by writing a k-frame. Set of all orthonormal k-frames. Orthonormal arbitrary vectors. K-frames are a set of k linear independent vectors. Oh.
Good for the other.
So it's the set of all orthogonal linear independent vectors. That's it. Nothing. Simpler than I thought, actually.
Yeah, seems like in other paper this is important. Just because you find a subspace doesn't mean you know how the data is from it. Yeah, no, I think I mostly look at like the things that I wanted to look at, and the many things is math, and it's kind of there's not that many results.
Block 1 represent-oriented curve lighting shows state around this structure.
I think this is nice. It's disappointing compared to the hype, but
Say again?
I think this is slightly disappointing for the amount of hype, but it's nice.
Maybe if we change the different methods together, that you get fully unsupervised manifold discovery.
Yes, yeah, we need something like that.
So
I mean, but yeah, but
You-
it seems like this is work towards that.
yeah. So you have this activation. Grasping, gain. Well, oh, okay.
Does anyone else have some take or something to say about the paper, by the way?
Okay, activation is resolved. You take the activation, you push it through this, and you get these different blocks. So each activation gets decomposed into different subspaces. Uh-huh. The norm of the blocks corresponds to how activated they are, right? So only those that are... So it throws away some that don't activate at all or something. Here. And if you then take these blocks together, sum them, then you reconstruct this. Okay. So residue is this, and that's the square. Okay, I think I get now the architecture itself. Yeah, it is literally decomposing into blocks. Right, yeah, into subspaces. I think I get the architecture now. At least the the data flow. There are still a lot of details I don't get. So block 1 can be, for example, cosine sinus. Like that. That forms a curve or something. Many examples you see that it forms this. That traces a circle. Because it's in 2D, since the block can be in 2D, and when you run all the different activations through it, you see that it forms a circle. There. It has one free parameter, circle, which is the angle, but it has two-dimensional linear span because it's in the two-dimensional ambient subspace. Okay. In what dimensions you don't have anything like that. If B is 1, it changes this traces a line on the circle. I mean, it is kinda unsupervised manifold discovery still, I think. Because these subspaces can form a circle, for example. But you have to localize that. You have to look at the subspace and find a circle. In similar way, how you have to look at, say, features and make it somehow semantically meaningful. So, but like, yeah, I guess you can also find the circles just from activations. So, meh.
They don't even say the dimensions of the manifolds that they automatically learn. Is it just constrained to like a certain amount of dimensions for each manifold they're learning?
That is a hyperparameter. Well, you can learn that is not that is learned because it depends how what is the manifold that you actually learn in the ambient space in the different blocks. So everything can just go into a line, and that would be a function equivalent to an SAE if it all would go just to a line. But it can go into a circle instead, which is not an SAE in that case. It's actually seems why no one did this before. I feel like this should have been tried before. I don't know.
Why nobody did what?
Just expand the SAEs like this.
Well, like a lot of people are trying their own SAE ideas. They're just something that wasn't thought of before. Nobody had the compute to do it.
Probably the compute.
There is not that many people trying things.
I think like the amount of people who are trying new things are probably like in the tens to hundreds at most for any given topic.
For like especially for like for example SAE coming up with new SAE variants. And yeah, it seems like there is a lot of SAE variants, but like if there was like 100 people doing that and they release one or two each, that will feel like the literature is full of SAE variants. That's basically not a lot of people, you know.
Well, it's because it's hard to come up with new ideas. Bernie should be coming up with new ideas.
I guess you could say that SAEs decompose the model into a lot of straight direction, and this decomposes the model into a lot of subspaces.
Yes,
and
that's how I understand it.
But how do they do the steering? Like when you have steering, you have the subspace, and in there the activation trace some low dimension space. So in order to do the manifold steering, they have to construct the manifold in the first place. How do they do that?
I mean, I think they steer like they move through the steering blocks in layer down to
So after training, you choose some learn block. You find every page where the block activates. You collect that. You plot it, and see and interpret it like you would interpret a SAE feature, but you have to still steer it somehow.
I think they just take okay, so I think they just take the subspace, they make some grid in some iterations in the subspace. Okay, they fit some other they do some other step. They fit a Cohen map here. I'm going to search what that is. This probably some way of
That is exactly how you get the manifold then. to get the geometry of the subspace. I think that's the unsupervised discovery part of the manifold then.
Yeah. Yeah, I mean, once you have some point in the subspace, you can you can like do the same kind of thing you do still of manifolds. You have the point that matches to some vectoring activation space, so you can just steer with that.
How do you know in what direction to steer? You do the thing that you mentioned. What was the method?
Yeah, here
Kohan
they
met?
took a Cohen map, but I'm going to ask Claude what the satellite that is. Okay, it's okay. So basically, they have some method to fit a 2D grid to a set of points, and they just run that on the activations on that subspace.
That's the Kohan. How do they
Yeah.
say it? Kohonen map. Kohonen map.
Cojones map. It's apparently
Self-organizing map.
also I ran out of cloth usage for this week. uh,
Unsupervised machine learning technique used to produce a low-dimensional representation of higher dimensional data. That sounds like machine learning.
yeah, but I think it's just a thing to use. You can use when you have. I think.
While
they-
preserving the topological structure of the data.
I
Huh.
suspect it only works because you have a subspace with few dimensions, and then you can do this kind of thing. You can probably also do splines and all that. You know, like the problem with doing that on the that doesn't work if you try to just do splines on the whole. I think the problem with trying to do unsupervised finding of manifold by just doing splines is that you cannot do it over the whole activation space because it's a sum of a lot of different manifolds. Assuming it's that, maybe it's something more complicated with non-linear stuff. But if even if it's a sum.
Yeah. Wait, is it the same Kohan map I'm looking at? Because self-organizing map is a type of an artificial neural network. Kohan map. Oh yeah, it's bitterless simple. Just use, you know what? Just let's use neural networks to find the manifold. I mean, if it works causally, so you use neural network to produce low-dimensional representation of a high-dimensional data set, preserving, and somehow you also preserve topological structure. So I guess that's some inductive bias or something.
Yeah, it makes sense. If you can use simpler methods or like methods that are no scalars, but if you have some smaller subspace that you think the actual manifold thing is on that subspace, you can run the kind of methods that you will use to find that kind of thing on small sets of dimensions that probably don't scale to a lot of dimensions.
By the way, I posted training process of this self-organizing map.
Oh, nice.
How it looks like visualized.
Yeah, I saw that on Wikipedia too. But yeah, seems like
I wanna see how exactly they do this in steering. So this is how they find the manifolds, using this map.
at least for the steering, yeah.
And then you steer by going on this manifold from this map. So you would say it's unsupervised manifold discovery then? No?
Yeah, kind of.
So you don't even do any PCA. Well, you can do that, but like if you do this, you're like, no methods to extract the manifolds work properly. So let's just do bit relation.
I feel like there should be a better method that just directly gets you the manifold somehow, but I don't know.
Yeah, I also think that.
But maybe this will inspire people to find something like that, and then you'll they'll incrementally get better. Or maybe the people will keep hitting their head about it, and then one of these days, they will ask Claude Fable 7 or whatever to find some better method, and we'll just output the correct one.
Yeah. Well, maybe if you want, I can now launch Codex to create a UI. It
Sure.
could deploy the model to some cloud in a round pot or something.
Yeah, that would be
Because
nice.
I don't think I have the hardware for that. I kind of, yeah. If you don't want to do it yourself instead.
Yeah, no, do it yourself. I don't even have Claude creators, and I definitely not going to do it manually.
Maybe they already have some UI. Quick
Is
start.
there anything more we want to read and to figure out on the paper, or are you leaving it?
I know. I'll now trying to look at an example of the steering, like how the data goes through.
Okay.
I think I'm gonna try notebooks.
It's just at this
notebooks.
point I'm not doing my stuff, but yeah, feel free to continue. More for when I stop the recording of that and when we switch to talking about the other stuff like
Yeah.
the anthropic thing. But yeah. If
Yeah,
you
I
want
think
me
it's
to share some part to go to, I'm mostly being very erratic on this. If you want me to go to some part of the paper in the screen, so people want to, if you are going to be the one talking or something, feel free to tell me.
yeah, that's one possibility. Yeah, I think I'll just quickly try to like UI is like front end is ultra easy to wipe code at this point, so
Okay.
that should be relatively quick as well.
And if one of you guys wants to summarize what they've learned today, I would really appreciate that.
Okay, as I understand it, well, there's other thing. This paper is some step in the Good Fire's direction of trying to find some way of that's better than sparse encoders, of figure out the discomposing the model's activations in some nice geometry thing, and
Right.
they have a bunch of methods that work in ways I don't completely understand, but they all are Block-Sparse Featurizers.
So is a lot of the prior work sparse autoencoders in this direction?
Yes.
Okay.
There is a bunch of previous Woodfire papers on this direction talking about how sparse encoders are bad and how things are represented as manifolds and all that, you know. But this paper, what it does, as I understand it, is it's making something like sparse encoder.
Oh, I see. Yeah, sorry for interfering.
No. Very good that you have a moment.
They're using diffusion model. So what you do, you
What
you don't.
model?
So they're using diffusion models here.
Diffusion
So
model.
you go in the direction of the manifold when you're doing the diffusion, I think. Clamping the diffusion's model activation to that state. Okay, let me see how they do that then. That's how they
Isn't that
steer.
just normal steering,
And what is steering in this context? Like navigating on the manifold or looking around? Like,
Yeah, well, if some activation is on like, I don't know, green dock part of the manifold, and the manifold corresponds to colors of docks, then you can go in the red direction.
Yeah, steering is if you take a small step on that manifold, which direction do you choose next? Like, kind of a
Yeah.
It's more
Right.
you have the direction, right? And once you have the direction, you can add the direction to the activations in some way of the model, and that should, if you have the correct, green dog direction, that should make the image model output the green dogs.
Okay.
Steering in
So-
general is just normally you have some way of telling what the activations of representing something are, and you try adding, increasing those activations in the model to try to see if that causes the model to output the thing you think they represent.
Yeah, right. So the different blocks represent the different manifolds. In normal SAE, you just increase the value of the. I think I get it now. You increase the value of the of the SAE feature. In this context, how something is activated, how the block is activated, is the norm of the block. I think. I think.
And by me, but couldn't you
So
have
you increase the norm.
more than one manifold in a single block though?
Well, I guess that can happen. Like,
Okay, so
you decompose it into the different subspaces. So if you decompose, just like with SAEs, you can have abstract concepts, you can have very low level concepts. So here you can have very abstract manifolds or very low level manifolds, depending on the dimensionality.
yeah, but I just mean you could have some block that has multiple, some subspace that has multiple manifolds on it.
Yeah, definitely. And yeah, so you steer by just increasing the norm then, or something like that.
The norm, what? The layer norm? The what?
The norm of the subspace.
The
When
norm.
you have a vector in that subspace, then increase its norm.
I think I need to explain. Okay, so basically this is Block-Sparse Featurizers are, you have a bunch of blocks that, the sparse encoders tries to divide the model in a small, that's the model's activations in a small set of directions. This tries to divide the model in a small set of subspaces. So it's like the higher dimensional version of sparse encoders. So it's like if you imagine the sports encoder dividing the model in a bunch of arrows that get added to a bunch of vectors that get added to get the actual direction. This tries to divide the model in a set of slices of certain amount of dimensions. Which that type of parameter they try with 2, 3, or 4.
Yes, it makes sense. That was what I gathered from the abstract and the summary of the LLM itself. That it's so it's a lower dimensional submanifold that you're looking at. That's what you call it?
Subspaces, but yeah.
Subspace, yeah.
In these
That's
subspaces,
the
the model
manifolds
learns to create manifolds, or it can not work instead, and the subspace can be noise or not something.
And what kind of things have they been able to learn and extract? So are there interesting, structures or geometries that correspond to this visual? Because we were talking about visual representations, right, in LLMs, right?
They have pretzel example, for example. I see. It. I continue to believe it is unsupervised manifold discovery because you can. Yeah. No. Yeah.
On but
Yeah,
so
I don't
the
know.
paper is mostly on image models. By the way,
Yeah.
they don't do anything if in LLMs here. There is another similar paper where they do stuff on LLMs.
But
Okay.
so, Usagi, did you look at the Cohen map? Yeah, I don't know.
No. Actually, I was just thinking how you can steer on the Grassmannian.
That's the Grassmannian exactly.
Oh, it's just the space of like subspaces.
Okay. Why does one of the methods? I didn't understand the different methods. Why does one of the methods have the Grassmannian in the name?
Grassmannian is a differentiable manifold that parameterizes the set of all k-dimensional linear subspaces of an n-dimensional vector space over a field K that has differentiable structure. That sounds like basically just the space of the subspaces then.
Yeah.
Okay.
It is.
Okay.
Yeah.
And why is one method called Grassmannian and other one isn't called Grassmannian, if I remember correctly in the paper?
Yeah, I don't know. The only thing is like in Grassmannian, like the encoder and decoder is tied. Like it's the same. Like in SA you don't have, you have separate encoder and decoder, but
So in vanilla it's not tied, and in Group Lasso they do something else.
yeah.
Yeah, I don't
What do
understand
they do in Group Lasso?
why the vainilla is not Grassmannian. Like, why is the Grassmannian called that? Like, don't all of them have subspaces and therefore have?
Because the thing is like when you project onto a subspace, like the norm depends on like the basis, like what basis you choose for that subspace. But in the Grassmannian case, like it is subspace like the basis independent. Like you can choose any basis. It'll give you the same norm, the projection.
Oh, that's cool.
It's extremely general structure then. Yeah.
No, I guess Catman maybe knew, but left. Does anyone know how it related to the other paper, the subspace aware autoencoders? I will ask Claude, but I don't have credits anymore. Seems like the same kind of thing.
Right.
I don't know if it's exactly the same thing, but
They use the map as well for steering. So that where you have a lot of concentration of the grid or something, that's that's where you go. Something.
Yeah, because I guess you cannot take difference of subspaces, right? Like, so that's the puzzle, like how you steer from one subspace to another subspace.
I think the quote unquote normal steering. Yeah, I'm not sure if they do it also through the norm there. Oh yeah. Collect its codes. These are states that the model is unit produced. Target can simply be this. Steering actualize activations. And clamp it. What it isn't clamping like isn't clamping reducing? How do they clamp the pretzel block exactly? They clamp. Transfer it for me. So that will be the steering part, and then these states not true. Unsurprised geometry tells them these states not shipping together. These two states are nearby. Concept my fault. Yeah, by default you just have to steer on the manifold, and you have to, just like with SAEs, you have to like use your brain to do quantitative analysis, quantitative labeling. I mean qualitative, sorry.
Steer on which manifold?
In either using the map or using, I guess you do it by increasing the normal of the activations in depth subspace. I'm now checking how they do it without the Cohen map, without the self-organizing map, since I'm not sure exactly how they do that. I'm also gonna start searching. What? The GPT just cloned and inspected the GitHub repo to answer my question. I didn't know it could clone inside it can? Unable to access. Could not resolve host GitHub. Never mind, it cannot. That would be interesting though. That CGPT could do that. Yeah, I would have to do that with Codex instead. To do that. So instead it's just trying to look at the code. So there's no, they don't say how they do the clamping. And I don't even see the word clamp in the paper. That's suspicious. So pretzel. Steering the pretzel manifold. We prompt for an image of a pretzel, then run 4 steps of diffusion while fixing the pretzel block to a particular value. Oh. Okay. So you fix the pretzel block. That's what they mean by clamping. So you always want pretzel, and then you change everything else, all other manifolds, all other blocks.
I guess it's you have pretzel, but like, is there a pretzel block, or is that block? I will expect if you are taking subspaces that is maybe, depending on how big, like maybe it's not monosemantic, and there is maybe there is some manifold that is monosemantic, but you will find more than one.
Yeah, like essays also are not fully monosemantic, so I would say this inherits a lot of these issues of essays. But it's more monosemantic than the original activations, I would assume. Wait, what do you mean? Fixing the pretzel block to a particular value, and then you visualize the points within the block.
I mean,
if you fix the pretzel block, then you cannot change it anymore. What do they mean?
I mean, don't they just pick some point in pretzel space, which correspond to some point in activation space, and then you do normal steering? Or am I misunderstanding something?
They don't talk about this kind of steering here, though. They just say that they run 4 steps of diffusion while fixing the pretzel block to a particular value. Oh, I think I get it now, maybe. No. And you change Visualize the points within a
Oh,
block.
the whole
confused.
space. What does it mean to fix a block?
That's exactly what I'm now thinking about. Like, does
If
it
you
mean
fix the norm, maybe?
fixing the norm, maybe?
Then you fix the norm, then you get a slice of points where the different configurations of the block have the same norm. Maybe? I don't know. You can ask
That would make
Claude.
sense, actually. Yeah, I think that would make sense.
That would make
that
sense, but I don't know if it's what they are doing, though.
Yeah. I'm not trying to ask them as well. I'm using the GPT 4.6 Sol Pro, which is much slower, but I think the answers are much better than the XI. I wonder if it's also better than Fable. Like, I don't know. Maybe it's jacked. And I'm running out of credits with the Pro model, even with the $100 subscription.
I don't have Fable anymore.
You have the $20 now, so I guess that's one Fable Pro.
No. I cannot use Fable anymore. They remove it from the $20 subscription.
Oh, right. They removed it completely.
Yeah. They are supposed to going to give us like $100 of Fable, but which
I still have it
like
in the
a lot,
$100
but it's
subscription.
actually it actually cost them my calculations it costed them like $20 actually, and it's just the same amount of Fable we will have on the on a month normally.
Oh yeah, never mind. Yeah.
But this uses is like doubling or subscription, which is nice. But they are not. They didn't do it. Like I thought they would do it today, but they didn't do it today. Probably when they have more compute, I guess.
Steer within a block. Sure. How do you steer within a block? Yeah. He steered along the manifolds within blocks in a more structured manner. Amazing how they steer, but they do not say how. To traverse it in a controlled way, we fit a Cohen map to the block manifold and intervene during sampling by setting the block's activation to each grid waypoint and generating one image per waypoint. Each grid waypoint. What is that? Exactly. The path traces a smooth moose variation in the activation space, and the resulting images are displayed. Distribution behavior can be computed, though it's evident that from our assumption, thanks to the group size of the variations is large, but stay on manifold in the block subspace. An arbitrary direction activation space could carry the generation of the manifold of the natural images and degrade it. Weren't you thinking about this, Victor?
Sorry? What?
There's a sentence. An arbitrary direction activation space could carry the generation of the manifold of natural images and degrade it. But movement confined to the block's subspace high-density regions does not do so, instead maintaining semantic relevance. So you stay in the high-density regions learned by the Cohen map. That is my understanding now. That's how you do the steering with the Cohen map, at least.
But I mean, okay. So my question is, does it? Like, if you take an actually arbitrary direction activation space, if you move in arbitrary directions activation space, does it look worse? Like, does it get like empirically what happens?
I know that's the case with images, with a language at least. If you steer too much, as for example, as well, you get nonsense.
Yeah, like I'm imagining on this example, if you are moving like comparing as a test, as like a baseline. Why did they
New
not?
hypothesis.
try as the null hypothesis baseline. If we move, take this. If we take this point in the space that seems to generate pretzels, and you move in a random direction instead of along the manifold, do you still get pretzels as long as you move not too long from it? Or like, how much is the moving through the thing method better than random at staying in the part of the activation space that outputs pretzels?
I see. Yeah, I think we can try that if you want as an experiment.
Why not?
I can deploy the diffusion model to Together AI or something, and
Yeah, I also want to, if you can get an interactive thing where we can just do things and see the nice images, could be cool.
Yeah, basically that would be
compare with
the
expansion decoder or
so,
something.
so first I would try deploying it to Together AI, which is relatively easy, and do inference there. I think Together AI supports that. The simplest possible cloud. Maybe there are some. I see. Yeah, let's do that now. I want to do that now. Okay, I'm still gonna check if the GPT will find like oh, exactly they yeah, I guess they do the map high density regions. I guess that explains it. When confined to the block subspace high density regions. So my guess is that like the map thing, like it looks around, and where there's nearest neighbor, that's where you go to. That would be my guess. Yeah, I guess that's another question I have. Do they talk more about the Wuhan map in the paper? I am convinced this is unsupervised manifold discovery.
I mean, I think this is a way you can kind of do unsupervised manifold discovery. I just don't think it's like great, kind of.
Yeah, I think it's.
I feel
it
like
is weird.
It's still not a method. Is there some reason why we cannot have some method where there is some, something where you have a bunch of manifolds and they add up to some activation and you optimize on that, or is the problem that that any nice way of doing that is just too computationally expensive?
I was thinking that why do they do the thing in the first place, the map? Why not do nearest neighbor?
Doesn't nearest neighbor just give you clusters though? You want some grid or
Or
something
just you look at
around.
Just you look at cosine similarity with all the different vectors and go in the direction of the closest one at each iteration.
I mean, but that doesn't get you manifold, right? That just gets you some point.
I mean, if you have activations like this, so on a circle like this, and they trace a circle, and if you do this going in the direction of a nearest neighbor, you will go in the direction of a circle.
I guess, yeah. I don't know if that works for all possible shapes, though.
Yeah, that's true.
Like,
yeah, distances break down in high dimensions. I forgot. Across all dimensions.
not only that, but even in the field in low dimensions, if you imagine some kind of like imagine some curve that like you don't go along the curve with the nearest neighbors. I guess I can do with
I mean, you go
me,
no because
no, because okay, let me draw a thing on the drawing thing.
Show me
You see the drawing
homework.
thing.
It is
So,
loading. Now I see.
so if the manifold is like this, like if it's a thing that's like has a close enough curve, maybe it's easier to like if you imagine
Yeah,
you have
it depends. I see. You have to really granularly tile the manifolds to be able to do this before the activations.
like if it's like this, it might be
Yeah.
that the nearest point jumps, jumps from here to here instead of continuing the curve.
Yeah, that makes sense. But I think in the limit, as
like
you tile the manifold, then in the limit you will go correctly. But in high
or if
dimensions, distances break down. So
and in more dimension, if the manifold is something, if some torus thing or something, like it has 2 dimensions, like there is more than one directions for the nearest neighbors to go.
yeah, you
Like the
could
thing you're
just
saying,
choose.
or only
I
works in the
guess.
one-dimensional ones.
I mean, I think that would be like choose the direction that you want to go to. That would be like on you. I think.
Yeah, I think already with you want 2-dimensional things that like already you have some of the methods like UMAP or whatever that gives you already some.
But maybe maybe the sum is just. I mean, the sum just creates another grid. Oh, you have the grid. I wonder if you train the sum on the example that you gave. How would that look like? I think it would also break this self-organizing map. Your example.
Well, so about
Maybe.
the empirical example, something cool here is that they seem like they find some manifold that finds like corresponds to shadows and lightning, by the way.
Yeah.
And they
Yeah, I've
can
seen that in the abstract.
compare to the ground truth because they are doing blender stuff where they have the illumination.
Yeah, I wanna see that example in more detail. So they can do less and more shade and lighting. Do they specify some implementation details? So they prompt the stable diffusion for a pretzel. They choose a particular actual realized activation from the pretzel block. That's the activation that you get from the prompt, I assume, of dimension B16. Hold the pretzel block at that value for 4 diffusion steps. Use UMAP only to display the 16-dimensional cloud. Oh, I guess the diffusion is always more pretzel, more pretzel, more pretzel. Then in the neural network. The broader spin experience describes setting the block's contribution of activation to selected manifold waypoints during sampling. What are selected manifold waypoints? They're repeating the same thing. SG, so look, stable diffusion computing activation selected layer. Reshape feature map into activation vectors. Apply code each activation with the Grassmannian Block-Sparse Sparse. How is it called again? Block-Sparse Featurizers. Featurizer. That is funny name. Read the pretzel code, replace with the target. What? I'm a bit confused. Exactly does it work in diffusion models where you steer with assays? You should just increase the activation. Why? What? That shouldn't change at all. This is weird steering. I don't get it. Why do they just like keep the pretzel block the same value instead of increasing its norm or something? Since in assay steering you increase you increase the feature latence here. You increase or decrease. How does this traverse the manifolds? Aren't you on the same? Aren't you just on the same spot in the manifold if you clamp it? Aren't you on the same spot on the manifold? You just clamp, just let it be the same value. That is my question. That is my confusing question. Does any of you know how to answer this question? So
Sorry,
let's see.
what is your question, Bernie? I was not paying attention.
I put it also in the chat. So like they apparently keep the pretzel block the same value increasing instead of increasing its norm or something. But in SA steering, when you steer, you like increase or decrease the value of the latence. So like if you just clamp it to stay on the to same value in the block, if the block is the same value, then like aren't you just
Oh no, but I
on the same
assume
spot in
that
the
they
pretzel
clamp
manifold?
it to the value in some pretzel example, right?
Yeah, but like if the input and output of the you do another diffusion, you have another activations.
Like
What
you
do you
imagine you do another diffusion with some random noise and you clamp the pretzel thing to the pretzel area.
Yeah, so in another diffusion, in another diffusion step, you could have bigger or smaller values of the pretzel block, but instead you just clamp it.
Yes.
And if you do this, the model will just iteratively add more pretzel each diffusion step or something.
Yes. Even if I know that prompt doesn't say anything about pretzels or whatever.
It's just weird. But
I mean,
this
isn't that
doesn't seem
just
like
like
traversing the
steering
manifold.
I mean, isn't that just like steering with, the steering factor one?
Yeah. Well, assuming there is no pretzel block each new diffusion step being one as well. I think the weird thing is here is that, well, they assume the block encodes a pretzel manifold, but when you do this clamping, you always stay in the same place on the pretzel manifold in the block. So even if you get different pretzels like this, those are because of the
Clamp it to different
the
places,
different
but
blocks.
I think that's the.
This is
I don't know. I think
so.
that's
This is
different points
steering
on the same block.
manifolds in the different blocks. No.
No, I think those are different. The different places are different points in the same block. I think you clamp it to some point to generate one of the pretzels, but like each pretzel is clamped to different points.
I mean, so you learn some weight in there that transform your activation to the subspaces, and then another weights that transfer the decode, so encoder and decoder essentially, and basically in the new step, so you do first step, you save the pretzel values of the pretzel block, and in the next step you just instantly output the same values from the pretzel block.
Doesn't have to be. You don't need a step. You can just have, or you get a bunch of steps. Okay, so you get a bunch of steps. You get. I think they just tried the random points maybe, and then we saw.
GPT saying I'm right with this. Is it being suffocantic? Your intuition is correct. Within one generation, fixing the block at one value does not traverse the manifold. The traversal happens across
I think that's what's happening.
generations.
Yeah, you fix it at some point, but you traverse the Kajere by generating a lot of examples on different points on the manifold. Which is just
Travel
like the
happens
manifold
across
steering.
the generations by repeating the experiment with different fixed block value each time.
Yeah. I mean, that seems like a straightforward to me, I think. The only thing is like how you get those points if they are random or you do the maps, you do something to. But yeah.
But then those different generations, as in if you do it for each, that just seems the same, like I say, or fix. But
yeah, I'm not sure what your question is exactly.
Yeah, I think I understand what you're saying. But are they clamping like the norm or the components of that block?
I don't know. I don't think they say.
Yeah, if they clamp the components, then yeah, you're right. It won't move anywhere in that manifold.
Yes, that is my issue.
Yeah.
So it is not manifold steering. So you're not steering the pretzel manifold if you do that.
Yeah.
I mean, so let's say this on the side. Okay, so you have the block, right? You have some point. You clamp in that manifold. So you have the you have the reconstruction, right? So you have a bunch of blocks at different points in each of the blocks. and adding all of those points gives you the activation, right?
Yes. If it
Okay.
reconstructs perfectly.
And you take some point in one of them. You clamp the model to always have that point, like have that point active, like in that block. You get that point. So this means that the second part of the BSF, like the unembedding part, will take the model. So we take that point and convert it in some direction in activation space that gets added with the directions in activation space corresponding to the other blocks.
Yeah, if the latents are always the same when you fix it, when you clamp
Isn't
it.
this equivalent to clamping and activate a sparse autoencoder feature to be its own value?
Yes.
But that's
right.
a way of doing steering.
Yeah, if you constantly have, like, I don't know, get feature 1 constantly, then yeah. But
I mean, the more usual method of steering is instead adding that feature, but like clamping it works.
So how would I see? How would I actually how would I actually imagine the manifold steering? I think they do that maybe later then, with the map, because they say you stay in the high density regions. That seems to me like the actual vector steering that they do later with the Cohen map. So this first one, that seems to me like just clamping. So it's just steering the pretzel.
No, but
I mean, yeah, I guess you could say.
No, but it's
but,
different.
like,
It's moving through different points in the subspace. It's not necessarily manifold steering. It's more like if they are just picking the points at random. It's like moving through the block, so it's like block steering or something. But it's like in the
Yeah.
end, it's like if it was a
It is a specific point on the manifold steering.
no, but each point on the okay, so each I mean manifold steering has to work like that. You cannot steering like manifold steering is always steering in different points on the manifold, and you show what happens when you move through the manifold. I don't know if I explained it correctly. Like the manifold steering part is taking all of the points, you make a lot of images, and you show what happens when you move through this to the thing. But like each point in the manifold is like the same as normal steering for the same reason that you tile manifolds with sparse encoders.
Hey, I think I'm. Okay. Okay, my understanding here, since you clamp it to the same value, then you you take a lot of images, then you do 4 diffusion steps with the same pretzel block value. So it's technically steering the pretzel manifold single point.
No, you take different points on the pretzel manifold and you steer different images with them.
Okay.
And that's what the figure is.
And you get the different pretzel points by.
They don't say how they get them. They might just pick them at random. Or at least not on the figure. Maybe they're spending on the actual part of the.
Yeah, they say here, like it's a stable diffusion, so it generates the pretzel. So they prompt it for an image of pretzel, then run 4 diffusion steps while fixing the pretzel block to a particular value. Oh, okay. Oh, okay. So they prompted for a pretzel in the, and then fix it to a particular value. And how do they get the particular value? Do they get the particle value from the first diffusion step, or do they get it from different pretzel prompts?
I think they just pick different points.
Yeah, maybe. So like
different
you
points are
generate.
random, and on the block.
Yeah,
I
okay.
think they just pick different points are random between the block,
So
with the idea showing activations inside this block correspond to pretzels, right? So you are just picking points and random in the block and steering with them and seeing what happens.
yeah, so yeah, I guess yeah, like, and the difference with the Cohen map is that instead of replacing with it with a fixed pretzel block value, they prompted for Hetman Coffee or whatever, and then steer across the grid coordinates from the Cohen map. So there, it is not just like this single point that's constantly the same in the pretzel block. It changes across these grid coordinates learned from the Cohen map.
No, yeah, but okay. As I understand the image in figure 14, is actually trying different points in the pretzel block too.
Yeah, and you get it by prompting for a pretzel and then fixing the pretzel block.
Yeah, but then they try different points in the pretzel block, I think at random, and then they do you map to plot them at lower. Yeah.
Yeah, I guess probably.
No, I think Burning's confused because if you clamp the components of the pretzel block, then it won't move within that manifold.
Yes.
Okay,
Right,
but I think you clamp to some point, right? So you imagine the pretzel block. Like imagine the pretzel block is 2 dimensions. You have a lot of points where you could clamp it to. A lot of, you can clamp the first dimension to be 0.1 and the second to be 0.5, and that's a point. And that will produce a pretzel. And if you put it at 1, it will produce a different kind of pretzel.
Then you're not clamping.
Yeah, but they don't do that.
Yeah.
No, I think.
Yeah, that wouldn't be clamping.
No, but they are okay.
Well, it is clamping, but like in different experiments, clamping different values in different experiments.
Yes, I'm saying they clamp the activation to that combination of things, like to that on the block, because okay, so fixing the pretzel block to a particular value, they said here, right? I understand fixing the pretzel block at a particular value to be a value of, the pretzel block is a subspace. It has a bunch of, has some dimensions. Each dimension is a number, so you pick one number for each thing, one number for each dimension, and that's a point, and you clamp to that point in that subspace. And the rest of subspace can be whatever they want.
Yeah, the other subspaces change.
Okay, so
in all the 4 diffusion steps, it has the same particular single value.
And then you pick random points and you generate an image. What image you generate when you fix 2 different points, and then you do you pick the points at random, and then you kind of do your map, and then you get this and show the images that you generate for each different point, and you show that for the different parts of the subspace you generate different kinds of pretzels, but they are all pretzels.
Yeah, but I don't think they pick random points in the pretzel block.
They don't
have
say
to pick
it,
some
but
manifold. Yeah.
no.
So maybe they get the block from just prompting for pretzel and extracting the value multiple times to get different values that they then clamp in other diffusion generations.
I mean, they don't say how they do, but no, I think they're actually moving through the block maybe at random, because the like the not in actual examples, because they are steering, they are not. Yeah.
For a generated image, they choose one target block state. And during the intervention steps, it's just replaced to that one block state. So within one run, it's clamped. But across generated images, you have different points on the pretzel manifold.
I think on figure 14, they're just doing the naive thing of moving, kind of picking random points in the block to fix it too. And then later they're trying to find manifolds on the other example.
Yeah, I would be interested in like in one image generation.
I feel like this paper
That
has a lot of math and it's nice, but that doesn't talk enough about the empirical part. I wonder if it's because the results are not great actually when you actually try and you try to steer. They don't look great. Or it is kind of like Ryan was trying, like put some examples and like couldn't. I mean, to be fair, he was also looking at, the numbers, count thing that the models are bad at. But yeah.
Yeah, it looks like ChatGPT converged to what we converged to, I think. That they eliminate one manifold point during one generation, but they choose different manifold points for different generations.
Ask it if it can figure out how they choose the points. I think they choose them at random, at least for the figure 14. I mean, for the pretzels. For the other thing, they find a manifold from examples with the Cohen map or whatever it's called, and then they move through that. But I think on the pretzel sample, they're just picking random points in the pretzel block. But I have the suspicion. I think I just read section 6 again, and I think they
That
have
one's wrong. Random points in the pretzel wrong sounds wrong because you wanna choose it. You wanna pick them on the manifold and not in the whole ambient subspace.
I think they still pick. I don't think they don't pick on the manifold on the pretzel.
Yeah, if they would choose on random, that wouldn't be steering on the manifold.
I think they are not steering on the manifold on example 14. I think they are doing it on figure 15, but not on figure 14. I think figure 14, if I understand correctly, is randomly on the manifold. But as ChatGPT, if I'm right.
On the ambient space, not on the manifold. Manifold is a subspace of the ambient space. Subspace of the activation space subspace. Space is subspace.
Is there no appendix that display more of the things? I think doesn't seem. Or okay, there's this experiment here. That's a different.
It may be also in the GitHub repo that there will be some like implementation details there. Grassmanian.
You can. I don't have Cloud crates, otherwise I will ask it to find that on there.
Visualize. plotting the concepts. Okay. Plain Adam. They don't use Adam W. Manian. Init, decode, encode, loss. I wonder if they have steering. Patch the grid. I don't see steering in the source code. Code loss, maybe visualize. Radial clip. Float X. Okay. Do they have steering there? Load images, sentence scale, train grassman, and encode and visualize. Model encode. Atoms. I don't think I see steering in this repo. You can just visualize the blocks. That's where it starts, I think. Ends, I think. So if we would wanna steer, we would have to implement ourselves, I think.
I mean, but does the code not have things for the steering part?
Yeah, there's no steering. There's training and visualizing the Grassmanian, but not steering.
But
I
like,
think.
do they just not have
I'm-
code for Sanction 6? That seems weird. And that just makes me more sus of the fact that it probably doesn't work very well and they don't want you look at it.
I skimmed it. Maybe I overlooked it, but I can't find it. Train the Grassmanian, extract and rank top concept manifold. Yeah, it's like it seems like they're just this basically. If you look at this
But
this
Ryan was doing stuff with that earlier and showed some images, so I wonder what he did exactly.
Yes, true. We can. Is he here still? No. Okay.
No, but you can.
Did
ask him.
you write your own steering code? Maybe he didn't steer it. Maybe he just prompted like 3 apples, 2 apples, and then just visualize the concepts.
How does the
For the pressure
visualization
figure,
work,
the
by the way?
paper.
How does they
Just
visualize
zoom up
the
again.
thing on the image? Is it just you take the parts of the image where the like when on the
PCA.
activations the thing is high, like the block norm is high?
Yeah, you take PCA of the contributions.
Oh, they use different colors for the.
Then plot the different PCA axis of the block, I guess.
Yeah, and as different colors. Okay. Where are the images?
For the pretzel figure, the paper does not give a precise sampling algorithm, such as take every 10th point, run k-means sample uniformly alongside using distance. Each target is an actually realized activation of the pretzel block. That sounds like they extracted from the prompts. That is, they choose target vectors that the model has genuinely produced, rather than inventing arbitrary vectors. So let's see if ChatGPT is hallucinating or not. Realized. Yeah, in figure 14 for steering results on a pretzel manifold, that's clear to actually realized activations within a block. Okay. In the follow-up, a head person coffee experiments, they fit coherent self-organizing map. They use the resulting grid waypoints as targets. After they use every grid as a steering target. Image pay waypoint and so on. Oh, each image corresponds. So that's the same. The image is just the self-organizing map cell. Then you generate one image per one waypoint. So you also clamp there. Oh god. I mean, sure. Like, you know, well, I think that's then attempt to do a follow-up. Like, if you wanna steer across the pretzel manifold. Yeah, how do they get it exactly though? Okay. I think it is steering on the pretzel manifold because the different points that you get are the different pretzels, but you still don't go into some direction. That is an issue. So you just sample randomly the manifold. Self-organizing map, I think. So in the self-organizing map, you
I mean, on the self-organizing map, they have figures, I think, going through the different the dimensions of the self-organizing map. But on the figure 14, I think it's random.
Huh. Do they do it in some systematic way? So you also random sample, right? Not go in direction. They say highest density points. Okay, let's see. Yeah, I wanna see more of the self-organizing maps then. Yeah, it looks like all the points, they don't look that structured, but still cool. Okay, I'm now looking at more of the empirical results. It's actually pretty cool. Feature realizations on recovered concept manifolds.
And there is not a lot of empirical results, unfortunately.
Yeah. Okay, so also the very first
There's
figure.
also there's this cool thing on they didn't show here, the robotics thing. There's only on the blog post, but not on the paper.
Oh yeah, that's true. Yeah, if you that's cool. How
There's
they
a table one, and
rabbit ears manifold, rabbit face manifold. Yeah, it is a manifold. It is a manifoldish because yeah. You see how the colors change.
yeah.
Continuously. So only from the visualization you see it.
But the colors are from doing PCA or something like that, right? Or like
Yeah. But it is still continuous. That continues moving.
yeah.
There changes continuously on the different parts of the image, I guess, or activates continuously on the different parts of the image. Or
Yes.
actually, so each point in the manifold is the block activated a different value.
Yes.
So did they like? How do they test this? Like, did they like ablate part?
So they
Did they
test
try
what?
to ablate the block? Like, how do they test it that it corresponds to the this part of the image? Did they like ablate the point and then see that
I
it
mean,
doesn't
they
generate
correspond
the
to the points in
ear?
the minimap. I think this is just like the value. This is just plotting the value of the point in the image, like the value of the block of the different as different colors, the value of the different components, when the MPCA or something like that, of the block on like they get the components from getting a bunch of examples, right? But they then for each like each part of the image will have some activations, right? I'm assuming I don't know how that architecture is like, but yeah, there's probably some different activations for different parts of the image. So just do run the BFS for each pixel or whatever, and it will give you different values for the block.
You
The same
start
way
with
you could
noise.
just do like the
You
sparse
go.
encoder one will be just you check in which part of the image the sparse encoder feature activates or not. This is the same, but apart from block activates or not, you get the different directions of the block.
Here you have like in this image you have the same rabbit over and over again. So it's just one generated image then.
Yeah, I think it's the same rabbit but different blocks, and they activate on different parts of the rabbit.
I mean, if you do this, okay. So if you let me read the blah blah blah. They activate over the image of a rabbit where darker means higher activation. How do you know that the feature is though related to that part of the image? Like you ablate that part of the image? Because like you either ablate the part of the image or you ablate the part of the manifold. And that kills the generation or something, I expect. As in you ablate rabbit ears manifold. How do they see the causality there? Because it's just a single image. I mean, maybe on the different generation steps. Because diffusion generates everything in parallel. Visual blocks of directions activate over the image for different locations within a block. Okay, in the sum you also so there is no experiment where in single image generation or in continual, like you generate one image, you go to one direction in the manifold to the left, generate one image, one direction to the left, generate one image. There is no experiment like this in this paper, right? You always pick random points.
Wait, can you repeat that? You don't always pick random points in all of the experiments?
Not random, but random points on the manifold, basically. As in, you sample them randomly. You don't try to go in the pretzel manifold to the one direction. In the different generations.
You do on figure. I think you do on figure 15.
I look at this and it seems like even there you just pick random points on the sum, but
No, but you do the Cohen map, and that gets you something that fits to the manifold. But you have the grid, and I understand that on this image, like one direction is moving in one direction to the grid, and another direction is moving in the other direction through the grid.
Yeah, like I would expect to move on the grid.
Yeah, I think the image is moving on the grid. That's why you see how it smoothly changes on that seems like the left direction means something and the down direction means something else. But it's kind of not great. Like at least the right left one on the coffee, for example, seems to make it darker.
Okay, yeah, that would make sense.
But yeah, it kind of seems like a mess. I understand why they don't put a lot of things on there. This is like the kind of thing that the team, like on the fracture representations, people will complain about.
Definitely.
I think that's partly because they didn't find the nicest way of finding the correct manifold and moving through it. Part of probably.
Like if you look at the very first figure, it seems like the rabbit ears manifold is like just a blob. It doesn't seem structured.
Oh no, but it does seem structured though, because so I think that's not. I think that's misunderstanding the figure, because so you have the rabbit ears show the thing that seems to make sense, because what does it means this image? This image means that on some point they have different pixels. We have different activations for the rabbit manifold, right? And they take in.
I'm a bit confused in this because, like, in diffusion, the input is the whole image, output is slightly more denoised image. And in this whole forward pass, you
But,
transform
what's the architecture like?
one
Don't
image
you
to
have
another.
something like tokens or something for each pixel, or you know you get
You have patches. Yeah, you have
you
image
got
patches.
yeah. So I think
Uh,
this is just for each image patch the activations. That's how you get the different colors. Like the color is on that image patch, like the activation in the subspace where each color is a different. I don't know if it's PCA or whatever direction on the subspace. And it seems like some direction on the PCA of the subspace when you plot it, like seems like the colors means things. Like on some parts of the year it has some color, on some other parts of the year it has a different color.
like the patches get all converted into hidden states. And then you do the attention over there and so on.
Yeah, but cannot. Are there no, you know, like in Transformers, you have subcomponents that correspond to different. Like what
Also,
is
is
the
there a bit
architecture of the
example?
Dino?
This,
If it's Transformer, I think I
well,
understand. If it's something
is
at
this
CNN,
Dino?
I don't know.
Is this Dino or
Probably it's
or
probably Dino.
Stable
I don't know if it
Diffusion?
touches, but it's probably Dino. I'm going to search Rabbit
Yeah,
and
that's
see.
definitely.
Oh, they show nothing about rabbits. Oh,
Okay, but
into the
they have
rabbit.
similar thing later in the figure 9, which is on Dino. I would expect it's on Dino. Concept geometry is so messy.
I'm confused why this rabbit thing has no.
Yeah, this is weird.
Why does the rabbit thing is only on a figure and they never mention it rabbit again? Why is this paper?
Yeah,
Why does this paper talk so much about the math and so little about about the empirical examples? I want to see more empirical examples. I
I'm
understand.
satisfied with the math. But yeah, I would also like more empirical examples. Okay, so in this, so in the sum when it's fitted, they go up and down on the grid, so that's moving on the manifold. Great. Okay, so the sum is good. Though I wonder with the figure 1 what exactly it represents.
Okay, I think this can explain how they visualize it. For each block, we overlay the patches it fires on a sample of images, coloring each patch by the first 3 principal coordinates of this contribution. I think this is just how it. I think this just explains how the thing works. That's the thing I was trying to explain because I think I read it earlier. Can you see the thing I'm sharing on the screen?
Map on the red green. Yeah, I see. Overlay the patches it fires on, which means you have to ablate the patch to see if it fires there or not.
No, can you not? You know, if each patch has its own activations, can you not just run the BFS on the patch and get the blocks to the activation?
I see. Yeah, I'm gonna try to look. Grassman. I hope he went touching a lot of grass and not that much math. Okay.
Yeah.
You say something?
No, I'm just like, I probably should read more. I never bothered to read the Good Fire papers that much because it's confusing manifolds and everything.
They are very math heavy.
How did your steering code project go, Bernie?
The
steering
I haven't
library.
progressed much there. Since I
Right
was
now,
doing
I got a Blue.Rapid grant for one of my projects, so I'm gonna do that one.
Wait. Like, I think it's also dependent on the, like, do they look at activations in the first layer? Because in this Dino thing, because like since it's like, which activations do they exactly do? I think, do they even mention that? I don't think they mention that. Since you take the whole image, you first convert it to patches, then you convert it to hidden states, and then you do all the attention and so on. So that's why I'm confused how exactly they map it. Okay, let's see. Like they really don't elaborate on that. So actually visualize one. Do they talk about ablation? There's no ablations. Well, technically the steering is ablations. Well, it's not really. It's clamping. I don't know. I would like some ablations and comparisons more with. I mean, they compare with essays just in the figure, right?
Yeah. But yeah, it's not. I feel like the paper has very, like the empirical part doesn't have that much.
And then they have the essay direction in the figure.
Like the empirical thing, they test some more statistical style things, but less on the actually, the stealing or whatever. Anyway, do we keep? Do you still have takes on this, or want to keep looking at it, or do we just end it here because it's been for 4 hours?
Yeah.
I feel like.
Yeah, I now want to figure out exactly how they visualize the first part, the first figure and the
Okay.
9 figure. So
I
now
think they
trying
just
to
have patches, and the patches can have activations, and use the BSF on them, which gives you gives you a bunch of blocks and how they are activated.
Like,
and
but like,
you take that as space. Sorry.
I mean, if you, I mean, this like you have to remove the patch now to see that it's causally relevant to the
No. You are not doing anything about causality. Yeah, this is just like plotting which patches have activations.
But the model sees the whole model at once. I mean, the whole image at once.
The patches have like don't the activations in the middle have patches?
Well, you've okay.
Like in the hidden states, do the hidden states have patches? Like what is the actual? What's Dino? Is it a transformer? Isn't Dino a transformer?
It's a vision transformer.
Okay, so if it's a vision transformer, then it has a bunch of patches that are different tokens, right? Or different positions, whatever you want to call them in the transformer, right?
Yeah. Okay, I see. Yeah.
So layer N,
It doesn't collapse it.
It has like an image. You can see it as like to put it like an image shape thing where each patch is like a what would be a token LLM, right?
Yeah.
And it has a dim model size vector that you can apply a BSF to, right?
Yeah.
Okay.
Yeah. They put each. Okay, because I thought they just they take all the patches and then they like compress it or
No.
expand it
I
so
think
that
you
you
just
lose the
put it.
information about the patches. But you don't do that. You have each patch has its own hidden state that you edit. I think.
Yes. No, you don't edit or anything. Each patch has its own hidden states, right? So if you have the hidden states on the patch, you can take some subspace on the BSF and see if activates or not on that patch, right?
Yeah. Yeah, that would make sense then.
You can also do it with sparse encoders, and that's this image, right? But the nice thing about the subspace is that they have multiple dimensions, right? So
yes,
the colors, as it says on figure 9, what they do is they take the overlay the patches it fire on a sample of images. Okay, so they color each patch by the 3 principal coordinates of its contribution.
Okay,
Yeah, so
that makes sense.
they just take the principal components and they say, okay, so this principal component is red, green, and blue, and they just color the image with those colors. So if a block activates, it will have color on that part of the image, and also it will have different colors depending on the different directions. And it seems like you plot that way, you get some nice colors that seem to represent meaningful things about the image, where For
Yeah, makes sense.
example, the rabbit ears are like more red under and more green on top.
Yeah. By the way, this is very similar. Like, if you look at the original Dino paper from 5 years ago, this is also in figure 1. This looks like literally the figure 1 is almost the same. Like, also on top of the abstract, if you go to the paper, where they also show the representations like this and visualize it in a similar way. But this is a completely different method, but still it's funny how it's the correspondence, you know.
Yes,
Here
but
it's just the
thing
attention
with
maps.
the image you show on that you sent, and it's more like the sparse to encoder one in that it's a single color image because it's the activation is activated or not, like the representation is activated or not, while
this is just the strength of the attention.
Yeah, while this is trying to use colors to represent the more dimensions from the manifold.
Yeah.
According to points is a manifold according to fire. I mean, I think they will say that the cloud of points are like there is some manifold that the points fall into, and
the points tile a manifold. So
something like that.
So that's why they created a spline fitting to tile it to create literally actually the manifold from the points, the points tile. I guess the self-organizing map is kinda also a manifold. Since it creates this grid. Good, actually, the self-organizing map, when I think about it. Like, instead of just looking at the points in weird ways like this, you just train on neural net to... I wonder how it works exactly. Like... If the loss is something like approximate the density correctly. I don't know. Get closer to points. Maybe. Okay, I think now I see most of the paper then. I'm also still curious, like what is the third method that they have? The lasso, I think. So lasso. Yeah, that just does some shrinking and removing. Shrinkage bias of convex sparsity penalties. I guess that's to filter noise. That's the reason. Okay, I'm gonna try to do the visualizing thing then. It'd be relatively easy. CD projects. Maybe the actually table diffusion, so maybe that will fit on my GPU actually. Think about it now. Also with the rabbit example, I think the GitHub repo has the rabbit examples in the code. Yeah. So with the rabbits, that's in the code, so we can check in the code exactly how they do that.
I mean, I think I understand how it works, but anyway.
Yeah, I think I as well do now. Yeah, so I guess one thing that one can visualize here is trying the different prompts and the different exact model do they use. They use Dino3. How big is Dino3? Space. Hmm. 1 billion. 21 million params. Okay, maybe that's why they do it on visual models, because it's very cheap. Very small. So now I wonder how to combine this with the JSpace. I guess you can take blocks of the activations run through the JSpace. Through the Jacobian matrix. Maybe. Is you're distracted by the Jacobian conjecture. He posted a few minutes ago. Maybe distracted even more. Yeah. Victor?
Sorry?
Can you hear? Yeah.
Yes, by that point, they started looking at the stuff out the Jacobian conjecture. The thing.
I just said to you, so that I see you distracted by the Jacobian conjecture. Yeah.
How did you see that? Did it show up on my screen or something? Or
You posted in memes the meme.
oh yeah. I mean, but yeah, no, feel free to continue on this
Like,
paper.
yeah, I think we can. I think we can end the paper.
Okay. I was mostly waiting for when you finish, so I can stop the recording if you don't want to. But yeah, I kind of got tired of paper a bit ago. I long ago, to be honest.
Say again, the last sentence.
Yeah, like I got tired of the paper a while ago.
Yeah, that's fine. I was also thinking of like now maybe like in terms of combining it with the JSpace, maybe I think you could technically just take the JLens on the blocks potentially.
Can you take in what sense? Because okay, so what does it mean to take the aliens on the blocks? What blocks?
You take the partial derivatives of the last layer with respect to the activations in the blocks.
Okay. That's still going to be.
So that takes into account how the different blocks influence the final output.
Okay, so how is different for the normal J-lens? You get some different vectors. Doesn't that get you the same? For some of the experiments, it's different, but doesn't for the J-lens specifically, don't you get the same tokens?
Well, slightly transformed.
Oh well, I guess the aggregation is different.
Instead of how the different instead of how the activations directly influence the last layer, you take in account how the different blocks influence the last layer.
Yeah, but like, don't the blocks add up to the activation such that if you take all of the blocks together, it gets you the same result?
Yeah, if you reconstruct it correctly. But
Yeah.
here you can more, I guess, localize more. So like you could have like only one block instead of the whole activations at one layer. So you can take in account not just how the whole layer influences the last layer, but how each of the blocks separately influence the last layer. I guess that could be one possible way. But I'm not sure if it would give something useful. Like I think one thing with
I feel like you need to redo all of the applications of the GLAs in this format. You know what it even means. You know, it's different.
Yeah, in the JLens you also like put everything into tokens in the end, so maybe there's a better way to put everything into manifolds instead of
Yeah,
the
like
tokens.
but here if you put in the tokens, if you then J-lens, you will if like what would you do? The J-lens for only one block, for example. You can also do the steering. So the way they do steering, I guess you could do also steering only on one block, but what does that get
I guess you
you?
could find if the JLens would read the same concept like the different either manifolds or SA features.
I mean,
That'll be
you
interesting.
could. Another thing is not exactly combining this well. You could see if the J lens aligns with either some SA features or some blocks. Like when you take the J lens vector for some token, does that correspond to some small set of features, either on blocks or sparse encoders?
Yeah, like you can just do separately SAs, separately JLens, and see if you get the same tokens that corresponds to the features in SAs. But yeah, I think more interesting is trying to replace the tokens with something like SAs or manifolds, so that the output of JLens is SAs or manifolds, SA features or
But
manifolds.
I mean, there is a features on the intermediate layers, right? So I mean, I guess you could do something like what, like find the vectors that make on some previous layer that make some later layer feature activate.
Yeah, you could take Jacobian between different layers.
Maybe that tells you something interesting. I'm getting tired now.
Yeah.
Sleep that well. I tend to not lately. I'm not sleeping that well on Mondays because I come from the weekend where I kind of stuff.
You go to sleep late.
Yes.
But even 5 p.m. is too soon. Or you don't
Yes.
sleep until 5 p.m. Or you do. Okay.
More than that. Yesterday I slept
At when? I didn't hear.
I wake up at I went to sleep at like 7 a.m.
Well, 7 a.m. to 5 p.m. That's still 10 hours.
No, 7 a.m. to 2 p.m. That's why I'm
Oh.
asleep now.
Okay, I see. Yeah, 5 hours for sleep isn't much. Oh, I need to... What? I need to agree. Share your contact information to access this model, to access Dino. Okay, sure, whatever. Because it's meta. Plays too much Final Fantasy.
What did you say about Final Fantasy?
You played too much Final Fantasy that you
I
went
haven't
to
been
sleep
playing
at
Final
7.
Fantasy much lately. I probably should have not played.
Okay.
I mean, yeah. Anyway, I'm going to stop the recording, by the way, if we are not talking more about that.
Yeah. I think that's good.